gracious, my nose is itching. Okay, must be going to have company. Any questions? Anything we've done so far? All right, now let's do a quick review of where we are, where we're going, where we're heading, how we're going to handle it today. Okay, we're in chapter 4, and the title of 4 is Heat and Temperature, and it's almost backwards because we're doing temperature kind of ahead of heat. Okay, and once we do temperature, then we'll do a few other things and then get to heat and sort of tie them together. Okay, not exactly that way, but sort of more that way than heat and temperature. Is more like temperature and heat. Okay, now that being said several times, what we'll do once we get more into this chapter, we will, oh, here comes iPhone. Okay, let me see if I can remember who iPhone is. I think it may be, I know who it is in one class, but not in this one. So I'm going to need someone to fill me in on who iPhone is. Just got into the class. Can anyone let me know?
Thomas.
Thomas?
Yes, sir.
Okay, got you. I'm trying to find you now, but I know you're here. There you are, Thomas Habrowski. Okay, there we go. Got you. Okay, you're holding down the top of the alphabet all by yourself there, so I hope some more has come in to help you out there. Okay, what we're just talking about, are there any questions on anything before we get started today? I am recording already. Okay, as I was saying, this chapter's title is Heat and Temperature, but we're very early in the chapter and we're already talking more about temperature than we are heat, so it's kind of backwards the way they say it, but it's okay. We'll talk about both of them. Now, I think most of the rest of the class time we will be in this chapter. There's quite a few calculations and other things we'll be doing, so I think that will cover pretty much what we need. Goodness, my nose is just itching like crazy. And then we will do the lab. Now, the lab today is more like 2 labs ago. Okay, it's more like last chapter's lab, whereas the lab we did on Tuesday actually had some heat and temperature associated with it. So actually I should have reversed those 2 labs, but I already had one done up as that lab number, so I went on and kept it. But I should have really reversed those. So anyway, the lab we do today will be more like the energy skate part that we had. This will be the pendulum lab, and it won't have as much to do with heat and temperature like the last lab, the lab we did on Tuesday did. So like I said, I probably should have reversed those 2. Any questions on anything we've hit so far? I do believe that we I was trying to think of something. One thing I do need to do is scoot y'all a little bit to the right here. Okay. Let me hit this next. I was going to wait until more people showed up, but maybe I'll remember to say it again when more people start coming in. We got an email from the dean either yesterday or day before that was, it sounds like the administration is beginning to panic a little bit. Right now, enrollment is sort of down. Well, and with COVID and with virtual classes and, technology infrastructure being what it is, it's almost understandable, but it's also worrisome to the administrators. Okay, and what she was recommending to us was do everything that we can to encourage you to go on and register for spring term soon, very soon, as in now, okay, to help them get their numbers up, because they've got to make some contingency planning, and right now they can't do a lot because the numbers are so fairly low. Of course, they took a long time getting the schedule out, and they kept changing their minds on things, that it was going to be virtual, then it was going to be on campus, then partially on, I mean, part of it is their own doing, I think. But there will be classes back on campus in the spring. I won't be teaching any of them because I'll be retiring on the 1st of February, so I won't be teaching any classes in the spring. I may fill in, just substitute, you might say, teach, if there are any classes that we don't have an instructor for in the month of January, but that's about all because I'm retiring the 1st of February. Okay, now, and that's part of their dilemma, is whether they hire people or not hire people. So it's not a really good situation. So please, if you are going to be here in the spring, please go on and register. Okay. This new banner system, at least, this fall was the first time we had been on it. And at that time, students couldn't register unless they had met with an advisor. And we have the virtual advising center out there, and there's somebody manning that center, I think from 8 in the morning until 6 in the evening, 5 days a week. So they should be able to get in touch with somebody, an advisor, sometime or another. And all they have to do is have that time with an advisor, the advisor that can then remove any blocks they have for your registering, and then you're good to go. In the old system, we could help students register. We could actually do the registration for them. This new system does not allow for that, but at least in the fall, it required them to see an advisor before they could register for a class. Now, I don't know if the same thing holds for spring or not, but if you haven't been able to register, that may be the reason, because you may have to see an advisor first. So please try to get that done sooner rather than later. Okay, that was my paid political announcement. Are there any other questions or concerns or issues? All right, I didn't mean to be killing time, but I was wanting to make sure that we have everybody, giving a little more time for people to show up. So I've got, I think it's, 6 students here, and make sure I've got 1, 2, 3, 4, 5, 6. Okay. Now, where we left off last time, we're in Chapter 4, Heat and Temperature, and right now we're picking up in 4.2, which is temperature. Okay. 4.1 is sort of just introductory, the kinetic molecular theory. Okay. 4.2 on page 91 if you got the big book. It's on 4.4-5 if you got the smaller book. Okay. And I think we talked about before the concepts applied moving molecules. No, I don't recall that we did do this one. It's a little blurb about it, and you're certainly welcome to read that and go over it. Okay. Basically what it says is blow up a balloon, tie it off at the neck so it will not leak air. Note the size of the balloon. Place it in the freezer part of your refrigerator for an hour. Then again note the size of the balloon. Immediately place it in direct sunlight for about an hour. And again note the size of the balloon. Explain your observations using kinetic molecular theory. Okay? You blow it up with your current temperature of your breath, whatever that is. Get a nice size of balloon. Okay? Put it in the freezer and you'll see it shrivels. Okay? Why does it shrivel? Because the average kinetic energy of those molecules, the speed of those molecules, decreases. Okay? Therefore, they bounce against the wall of the balloon with less force, less pressure, and the balloon collapses to a certain amount. Okay? Take it out of the freezer and then put it in direct sunlight, and watch it grow, okay? And it goes back to either its original shape or even larger. Why is that? Because in the sunlight, now the molecules are moving faster, they're bouncing off each other faster, they're hitting the walls of the balloon with more energy, average kinetic energy. That is temperature. Temperature rises, more force per unit area or pressure is put on the balloon, and it gets even bigger. Okay, so that's the kinetic molecular theory at work. Sort of a fun thing to do and see. All right, then let's start with 4.2. I'd hoped there'd be more students here by now, but I'm glad y'all are here. We just got enough for a volleyball team. Okay. What is temperature? It's a measure of the internal energy of an object. The measure of the internal energy of an object. Specifically, the average kinetic energy of that object. Okay, that's the internal energy we're talking about. Now, how do we measure temperature? We use devices called thermometers. Now, if you look at the word thermo, basically means heat or temperature. Meters is to measure. Okay, and what thermometers are objects used to measure temperature. Thermometer. Okay. They rely on certain thermometric properties. Okay. Now that's sort of a nebulous sounding statement there. What do we mean by that? There's not really a device that measures temperature. It measures something else that responds to temperature. For instance, the standard old thermometer that you may have seen growing up or actually used, and if we were on campus and doing our labs, you would be using these. They are long tubes of glass or plastic that have some sort of colored liquid in it. Some of them are silvery, that's mercury. Others of them are reddish, that's usually alcohol dyed. Okay, some very easy to read alcohol. What they're measuring then is not really temperature. You kind of are. What is happening there, if you put that thermometer into a beaker of ice water, you'll see the level decrease. What are you measuring? You're measuring the thermometric property of the contraction of a liquid when it cools. Or put it into boiling water and you'll see the liquid go up in the tube. What you're measuring is not really temperature, though it's scaled for that. What you're measuring is the expansion of a liquid once you heat it. Just like we were talking about with the balloon, the air inside collapsing when it cools, expanding when it heats, the same thing is happening to that liquid. It expands when it heats, it contracts when it cools. So you're relying on the thermometric property of expansion or contraction of a liquid. Okay? Now, here's another one. If you've ever seen the thermometers that they have an arrow on it and a face, I'm going to have to go. I'm sorry. We just started class and my nose has started running and I don't know why. Let me pause the recording for a moment and go get me some tissue. I'll be right back. Okay, that's one example. Oh, here's Jacob. I hope he wasn't waiting long. That was the trouble with having to leave the classroom. I may miss people coming in. And sorry, Jacob, if you're waiting long, but I had to go pick up some tissues. Just all of a sudden my nose started running. So let me make sure nobody else is waiting. Nope, we've got 7 students now, and I think that's how many I've got on the roll book. 1, 2, 3, 4, 5, 6, 7. Got it. Poor old Thomas up there is holding up the whole top part of the alphabet by himself. The middle part is doing pretty well. Bottom part's all right, but the top part's pretty sparse right now. Now, another example, I was just going to say, if you've seen these thermometers that are usually round and they have a needle, and as it warms up you see the middle needle move, say, to the right, okay, and it's scaled somehow there. What in the world is making that needle move? The needle doesn't move directly because of temperature. It moves because, again, the expansion of a material. Your liquid thermometers, as thermometric property, would be the expansion of a liquid when it heats and the contraction when it cools. These are bimetallic strips and thermostats. Now let me see if they have a picture of it here. It's not showing up. If it is, yes, there's a bimetallic strip. What you have is iron on one end of the strip, on one side of the strip, and brass on the other end. Or it could be other metals, but this is a typical one. And if you put that under heat, okay, at room temperature you have a flat strip. Put it under heat, and what happens is the brass expands more quickly than the iron does. Iron expands more slowly. So therefore the difference between those is going to bend it upward. Now if they expanded at the same rate, it would stay flat, but they don't. Iron expands more slowly, brass more quickly, and it bends it up. Well, that's what's happening. Just turn it sideways. That's what's happening in that thermometer as it moves up. The bending of that bimetallic strip, and bimetallic means two metals, in this case iron and brass, okay? Now that's also what they use in thermostats, okay? And I don't think it shows in your book. Let me just see. I mean on the slide set. No, it doesn't. But here is the inside of a thermostat, at least the old kind. And you see this strip, this coil over here? There's a bimetallic strip. Now whether that's iron and brass, I don't know. I'm guessing it probably is. At least the brass part looks like it might be true. And that, as it heats, it expands, and because they have it in a coil, it's magnified. And basically what happens is, hard to see it with this, but there's a vial of mercury that as it tilts, then that could either turn on a switch that might turn on your heater if it goes one way, or turn on the air conditioner if it goes the other way, okay, depending on that bimetallic strip. So that's used in thermometers, but also used in thermostats to help regulate and control temperature. All right, any questions on temperature? Okay, the next topic here are some of the scales we use for temperature. Okay, this is on page 92 or 4-6 if you have the smaller one. Now before you get to it, there's a little blurb saying concepts applied. Does a human make a good thermometer? Not particularly, okay? And the reason for that, and we used to do a lab, it was sort of a messy lab, so I quit doing it, but we're not doing it at all now because we're not on campus. But I would have 4 containers of water, okay? Have a thermometer in at least 2 of them, okay? And I'd have students place their hands in those 2 of those containers of water, okay, and read the thermometer and see what that temperature felt like. And then once they got a good idea of that, then move them real quickly to put their hands in the next 2 containers of water. And that one, they would estimate the temperature of those containers of water, okay? And then we'd move the thermometers over and see how close they were. Most of the time they weren't really very close, okay? So humans don't make very good thermometers, okay? So that's what that little blurb was about. You can certainly read that and note that, and you can do it at home. It would be fine. Now let's talk about temperature scales then. These are defined, and when you see the WRT, that means with respect to various reference points. And unfortunately, that's a big problem for us because historically, people have used different reference points to measure temperature. I'll try to go back to the first pretty successful thermometer ever developed, and this was by good old Galileo. I don't know how much you've been around a chemistry lab, but chemistry labs have all these different kind of beakers in them. And this one beaker is sort of bulbous on the bottom, but goes up in a narrow column at the top. Okay? And good old Galileo put a fair amount of water into that beaker and had a pan sitting down underneath it, flipped the beaker over into the pan, and so there was continuous water there, and he made himself one of the earliest decent thermometers. Because what happened, the air expands more quickly than water does with temperature. Okay? So when the air in the top of the beaker, once he flipped it over and that bulb that was there, up there on top, the air would expand and it would push the water level down. Or it would cool and suck the water level up. Okay? That was an early thermometer scale. Okay? Now, depending on how narrow the beaker was, that neck of the beaker, and how good he was at putting things in there, he could sort of have a pretty good scale defined with respect to various reference points. Now, I don't know what he used as his reference points. I wouldn't be surprised if he didn't use ice water as one reference point and maybe something pretty close to boiling at the other. I don't know. Never have read or understood exactly what he used as his reference points. But he had a problem with it. Okay? Sometimes the same temperature would read different levels on the neck of the bottle, and he didn't know for sure why. Now, he may have figured it out in time, but I think it just bugged him. Okay? Does anyone have a clue of what was messing up his readings? Because he had a pool of water at the bottom, barometric pressure also would influence that. Because the barometric pressure, if it's high pressure, it pushed down on the water, compressing the air in top, giving him a false higher temperature. No, I'm sorry, lower temperature, because that would be like it's contracting the water. Or when it's a very low barometric pressure, then the water would be pulled out of that, giving a false high temperature. And that was his problem with his early thermometer. It did not distinguish barometric pressure from temperature. Okay, but guess who took care of it? Good old Isaac Newton came along, the next generation, born basically the same year that Galileo died. Of course, it took a while for him to catch up, but anyway, he perfected that by putting another liquid, probably not water, okay, into a tube, a capillary tube, filled it up, then flipped it over and sealed it. And by sealing it, that wiped out the ability of barometric pressure to change it any. Okay, so then all you had was the expansion of the liquid rather than the expansion of air, and that's what led to a better reference level. Okay, reference points. Now again, I don't know exactly what Newton used, but it seems like sometime or another I read that he used the freezing point, the lowest point was the freezing point of water. That was where water and ice are in equilibrium with each other. And then I think he had as his upper limit body temperature. Now, not a good choice, but that's what he was using, body temperature. And of course, not every body has the same temperature. I worked with an engineer down in Florida when I was at Southern Research Institute, and if she ever had a temperature greater than 97, she had a fever. Most people, it's 98.6 is normal temperature. Her normal temperature was 97 degrees. If she had a 98.6, she was sick. Okay, she had a pretty high temperature. Okay, so not everybody's, that's not probably the best thing to use as your reference point, but he chose that as his reference point. Now he also, I hope I've got that right, used the difference there of 12 degrees in between the freezing point of water and body temperature. He said, let's just make that 12 degrees, because he didn't have really great um, thermometers, so he had 12 degrees there. Well, as they got better and better degrees, people started taking those 12 degrees and splitting them and making smaller degrees, okay, because they could be a bit more precise in their measurements, okay. So they first went to half degrees, and then they went to quarter degrees, then they went to eighth of a degrees. Now that was getting pretty small then, okay. So they quit calling a degree and started calling an eighth of a degree, if that makes any sense. So if you take 8 times 12, that got you up to 108, okay? So basically his body temperature was right around 100 degrees, a little bit more than that, 108 degrees, okay? Now, along came Fahrenheit. Fahrenheit was a German physicist, and he was working with all kinds of different materials, and he had noticed something. If you had something dissolved in a liquid, it typically depressed the freezing point of that liquid. Now, I bet you most of you, or some of you anyway, have probably experienced this. Have any of you ever made homemade ice cream in the summertime? Yay or nay? I hear no response, so I don't know. We've made it many a time. Both my wife and I, since we've been married, and I can remember back when I was a boy child, you know, on the farm, we made ice cream there too. Now, if you've ever made it, you know that if you put the cream and the eggs and the sugar and the whatever else you're going to put into that, and just put ice around it and try to crank the ice cream maker, you know, so you would get very cold cream. Not ice cream, but very cold cream, because it would never ever freeze. The ice itself would not freeze the ice cream. Does anyone have an idea why? That milk, that cream, the sugar, everything else, you're mixing things with the water. Say that again. Okay, you're absolutely right. I wouldn't quite call them impurities, because that was what made it good, but other materials dissolved in it or suspended in it to keep it from freezing. You're absolutely right. Okay, so what do you do to make the ice cream freeze? If you can't just use ice on the outside, and here's somebody coming in, can't see who it is, I'm thinking Angelica, and let me see, Angelita, I'm sorry, I mispronounced her name. Angelita, I believe that's who's coming in. All right, so Thomas has some help on the top of the alphabet there. So that gets us up to 1, 2, 3, 4, 5, 6, 7, 8 students here. Let me make sure we got everybody. Yep, 8 students it looks like. And let me scoot up here. Yep, Angelita is here. Good deal. Okay, so believe that was Jacob answering that. He was right on the money with it. You had more things that were being dissolved and mixed with the water so it wasn't freezing at as low a temperature. Now the question was, how do you make that freeze? Anyone know? You put something on the ice. What did you put on the ice? Salt. Rock salt or table salt, it didn't matter. Rock salt was cheaper. That's what my dad always used. He always went the cheapest route. It didn't get into ice cream. It was just on the ice, and you're cranking the thing around, the metal cylinder that contained the good stuff, but the ice and the salt was on the outside of it. Now what did that do? Well, that's something else dissolved in water, or was going to be dissolved. It depressed the freezing point of the ice. So now that ice was melting at a lower temperature than it would have had it just been ice. Okay? And if you've ever noticed that, it was at such a low temperature, the old style things, you would sometimes get frost being built up on the outside of your ice cream maker because it was that cold. Well, Fahrenheit was messing around studying different materials that he was mixing with ice to lower the temperature. So if your ice water or ice was your lowest end of the scale, then he was having to have negative numbers. And Fahrenheit, like many of you, probably didn't like negative numbers. He wanted a number much lower so he wouldn't have to mess around with negative numbers. Well, he used, I guess, the salts or whatever he used in his lab, and he wanted as cold as he could make it in his lab, that to be the 0 level. Well, that's the scale we still use, Fahrenheit scale, and that happens to be then the pure water, not salted water, but pure water will actually freeze at 32 degrees Fahrenheit, okay? Not at some lower number, okay? 32 degrees Fahrenheit. So that's how that happened. Still using the upper limit to be something close to body temperature. Now it's no longer something close to 108 degrees or something like that. Its body temperature is now going to be something like 98.6, which is pretty close to 100. Okay, so that's the Fahrenheit scale. Well, along came Anders Celsius. I believe he was either Swedish or Norwegian. I don't remember which. Somewhere in Scandinavia, I'm pretty sure. And he basically was hearkening back to more like probably what Isaac Newton did. He wanted something that wasn't, well, Isaac Newton had body temperature. He didn't want somebody's relative thing. Fahrenheit, maybe he could use a different material, then he'd have a different 0, okay? So Celsius wanted to get something very standard, like the freezing point of water at the lower end, the boiling point of water at the upper end, okay? They hadn't used that before. This is what they used. So he split his scale into 100 equal degrees. 100 equal degrees between the freezing point of water and the boiling point of water. So at first they called that the centigrade scale because centi means 100. So 100 grades or 100 degrees in between those. But later they named it the Celsius scale after Anders Celsius. Okay. But that didn't get rid of the problem that you had with negative numbers because, again, freezing point of water isn't as cold as you can go. Well, along came a guy named William Thomson, who that was his name, but he was a lord in the British system, which is very rare to have a really brilliant scientist also be a lord or a lady or something like that. He was a rare combination of brains and nobility. Okay, a lot of time the nobility isn't all that bright, So anyway, I'm sorry, I shouldn't be saying that. If any of you happen to have cousins or things that are princes and things, I apologize. Okay. But anyway, Lord Kelvin, that was his title, came along, and I think I described this to you before, but if not, I'll describe it now. He was doing several studies with volumes of gases, and he was taking a gas, a known gas, and it would have a known, at a fixed temperature, it would have a fixed volume. A lot like that balloon we were talking about earlier. Then if you drop the temperature of the gas, the volume went down. Drop it some more, it went down. Drop it some more, it went down. And he found out that those decreases were basically very linear with temperature. So you dropped a little bit and it dropped a lot more, you dropped a lot more. So it was very linear in its drop. Until it got to some point, and when you got it cold enough, suddenly it went to a liquid and the volume almost went to zero. But up until that point, as long as it was a gas, it followed a certain pattern. Well, say hydrogen gas did this. Nitrogen may have done this. Oxygen may have done this. Different gases did different things, different slopes of the line. But guess what? Where they were heading to all seemed to be the same point. Even though some of them were flatter, some of them were steeper, they all tended to go to the same point. So he concluded that there is some lowest temperature that an object could be dropped to, and at the time they thought the reason it was going to zero is all motion would stop then. Now that's a very, very, very cold temperature. And in fact, now that quantum mechanics is sort of considered to be the law of the land, they know that it never stops. The motion never stops, but you reach a minimum energy level. You always have some motion, but it's some minimum energy level. But anyway, that they named zero on the absolute scale. Why absolute? You can't get any colder than that. You cannot have a negative temperature, because that temperature down there at the very bottom, no matter what the slope is, that temperature down there is as cold as you can go. Now, we'll later talk about the laws of thermodynamics, and William Thomson developed those mostly. He had help and collaborated with others, but he was the big honcho who did those. One of those laws of thermodynamics, I think it's the third law, is absolute zero can be approached but never reached. Okay? And the old days they thought that was because all motion would stop, and all motion can't stop. Well, quantum mechanics also agreed that it can't stop. But now it doesn't mean all motion stops. You reach the lowest possible energy level. And that's what absolute zero is. Okay? So there's another scale. Now, the Kelvin scale. How do these relate to one another? Well, the Fahrenheit scale is almost half the size. A degree in Fahrenheit is almost half a degree in Celsius. Not quite, but close to it. And here's why it's not quite. Okay, I haven't given you this temperature yet, but let me give it to you now. On the Fahrenheit scale, water freezes at 32, not at 0, but at 32 degrees Fahrenheit. Water boils at 212 degrees Fahrenheit. Now, I am going to, there will be a picture in the book on this, but let's do it here too. Why this scale, this chapter, they use dark as the background, I don't know. So I'm going to, if I can get my, I can't get, okay, sorry about this. Let me, there we go. I'm going to use a very light colored pen here, like yellow, so it'll show up better. Okay? Now, water freezes at 32 degrees Fahrenheit. Water boils at 212 degrees Fahrenheit, or pretty close to it. What's the difference then between the boiling point and freezing point of water on the Fahrenheit scale? 180 Fahrenheit degrees. Oops. 180 Fahrenheit degrees. On the Celsius scale, we already know water freezes at 0 degrees Celsius and water boils at 100 degrees Celsius. So what's the difference between those scales? 100 degrees. Okay? 100 Celsius degrees. Well, what's the ratio of that? And it doesn't matter which one you put on top. A lot of people will put the 180 on top. It doesn't really matter. 180 degrees Fahrenheit covers the same range as 100 degrees Celsius. Okay, what's that ratio? Well, you can divide out the zeros there, and then this will be 9 to 5. An old Dolly Parton song, right? Okay, there was a movie they made with that. Okay, I think Lily Tomlin and a couple other pretty good actresses in addition to Dolly Parton were in it. Okay, 9 to 5. That's a ratio you need to remember. 9 to 5. 9 degrees Fahrenheit is equivalent to 5 degrees Celsius. Not quite 2 to 1, but close to it. Okay. Now the other issue you have is that water freezes at 32 degrees Fahrenheit, but at 0 degrees Celsius. So your endpoints are different as well. All right. Now let's get back to the Kelvin scale. Notice for Fahrenheit and for Celsius, I wish I could get the pen to show, there it is. Fahrenheit and Celsius, we refer to degrees. Degrees Fahrenheit, degrees Celsius. That's what the little circle, superscript circle is, degrees. Kelvin does not ever use a degree symbol. You just give it the number. Oh, and here comes Rodrigo. He was already here. He must have gotten bounced out and is back again. I'm glad you're back. Okay. Now, I'm going to have to pause for a moment here. Thursday afternoon, I'm losing energy awfully fast. Okay. Hopefully that'll boost it a little bit. Kelvin does not use a degree symbol. You just say some number K. Okay. 200 K. Here, degrees Celsius, degrees Fahrenheit, never use degrees with Celsius. It's whatever your number is, K. Now, they had to decide where, we know where the 0 is for Kelvin. That is absolute 0, as cold as you can ever go. You know you can get below 0 on Celsius. You know you can get below 0 in Fahrenheit. 0K is as cold as you can ever get. In fact, you can't even get there. You can get close. Now, I've read it before, and it's just amazing to me. They say you can get within a few billionths of a degree of absolute 0, but you can't quite get there. Well, whose thermometer can measure anything to a precision of a few billionths of a degree? I can't even imagine it. Okay, but theoretically you can't get there. That's the third law of thermodynamics we'll talk about later. Okay, now that happens to be about negative 273 degrees Celsius. That 0K is about negative 270 degrees Celsius. Okay, which, let me make sure, yeah, I do that right. Okay, so those two are equivalent temperatures right here, 0K and negative 273 Celsius. If you were getting this up to here, you move 273 degrees up here. That means on the Kelvin scale, you move 273 K. The point here being a measure on the K scale is exactly the same size as the measure on the, oops, Rodrigo is back again, okay? He must be having trouble staying in or something because of at least the third time that he's come back in. Glad that he's making it back in. Sorry he's having the difficulty, okay? So the freezing point of water on the Kelvin scale is 273 K. Never degrees, just 273 K. The boiling point of water on the Kelvin scale, absolute zero scale, is 373 K. So a Celsius degree is the same size as a K, a single K. Those are the same size. A Fahrenheit degree is less than, a little bit more than half of that, okay? That ratio of 9 to 5 or 5 to 9, okay? So those are your scales. Now, what is the relationship? How do you go between one scale and the other? Whoops, I'm on the wrong thing. I'm going to erase my scratch here. And let's see, here it is. Okay, popped right up there. Here's what we were just talking about. Okay, I may need to get a darker pen now because I don't think you'll be able to see. Well, I'm on the wrong pad. Yeah, you can't see it there. So let's go back to a darker pen, like maybe black. Okay, yeah, there you can see that. Now, on the Fahrenheit scale, the freezing point of water is 32 degrees Fahrenheit. The boiling point of water is 212 degrees Fahrenheit. So the difference there is 180 degrees, and that's the Fahrenheit degrees is the same as 100 degrees Celsius. So that's a ratio of 9 to 5. A Kelvin, however, don't ever say degrees Kelvin. Kelvin, I'll sometimes slip up and say it, that would be 273 would be the freezing point of water, 373 the boiling point of water. Okay? Now notice this, absolute zero has a very lowest point. There is no highest point that anyone's been able to determine. Maybe theoretically there is somewhere, but no one's been able to determine what if there is an upper limit on temperature. There is a lower limit on temperature, and that is your absolute zero. Okay, that's 0 K, which would be negative 273 Celsius, and believe it or not, they can measure this to be negative 459 degrees Fahrenheit. Now, back when I was in school, they used to have us learn another scale, and that was called the Rankine scale. The Rankine scale, the temperature degree was the same size as a Fahrenheit degree. So a minus 459 Rankine would be 0 Rankine, an absolute scale, and then you would go from there. Okay, add 459 to it, and you get 0 Fahrenheit. Add another 32 to that, and you get the freezing point of water, and add 212 degrees to it, and you would have the boiling point of water. Don't worry about the Rankine scale. We're not going to mess with it. But here you see those relationships. 180 degrees difference, delta T in Fahrenheit is the same as 100 delta T in Celsius, which is the same as 100 delta T in Kelvin as well. This is the one that's 9 to 5. Okay, now that gives us at least a leg up on how in the world we make our conversions. Okay, so here are the conversion formulas, first from Fahrenheit to Celsius. So you know what the Fahrenheit scale is. Okay, now I'm going to go back to my yellow here, because that shows up the best here. You know what the temperature in degrees Fahrenheit is. Whatever it is, you know that. Okay, what you need to do is multiply that by, this is sort of how we did. Remember, you put degrees Fahrenheit on the bottom, degrees Celsius on top. Okay? Whatever you started off with Fahrenheit, you're going to do that. Okay? Now, what this is going to do is give you how many degrees above. Okay. You need to make one adjustment first. And here's what it is. You need to start at the same level, 0. So how many degrees Fahrenheit, to match how many degrees Celsius, you need to know degrees Fahrenheit minus 32 degrees Fahrenheit. If my pen would write. So that's where you begin. Whatever your measured temperature is Fahrenheit, subtract 32 from it. That's how many Fahrenheit degrees you are above the freezing point, okay, because that is the freezing point. And then what was our conversion here? 9 Fahrenheit degrees for every 5 Celsius degree. Okay. So that gives you your formula. Okay, and then this difference in degrees Fahrenheit will cancel out the degrees Fahrenheit here, and this gives you your temperature in degrees Celsius. Okay, going the other way, you're starting with degrees Celsius, okay, whatever that is, and you're multiplying by that, blank blank, okay, okay. Now, what that would give you, and by the way, the second blank here is your units, and you would need degrees Celsius in the denominator, degree Fahrenheit in the numerator, so the degree Celsius would go out. And why is that happening? Okay. Excuse me, I'm going to have to get something else. My energy level is dropping drastically. Yeah, sorry about that. Okay, now what this gives you is how many degrees above the freezing point of water, and you're divided by the, and what's that ratio? 5 degrees Celsius for every 9 degrees Fahrenheit. Okay, so what this gives you is how many Fahrenheit degrees you are above the freezing point of water. Well, that you have to add your 32 degrees Fahrenheit to get that to make sense. Okay, because the freezing point of water is 32. The number you get here is how many degrees above the freezing point of water you have. So you add 32 to that to get that. So these are your formulas. Okay, now this is a little messy looking here, but that's how you can think through it. I hate memorizing things, so I use think through it. Okay, now how about Celsius to Kelvin? Well, we already had that one. We know that 0 Kelvin is equivalent to minus 273 degrees Celsius. Okay, so therefore 273 Kelvin is the same as 0 degrees Celsius. Okay, now and anything else. So what's the answer here? Kelvin, if you're starting with degrees Celsius, degrees Celsius and you're trying to get to Kelvin, what you do is add 273 K. So whatever you started with here, add 273 to it, and that's what your answer is in K. Okay, so there are our three formulas. And guess what the other way is? If you know what Kelvin is, subtract 273 from it and you get degrees Celsius. Okay, just think through that, and I think you pretty much got it knocked. So I'm going to erase my scratch here, and let's see if they give you these formulas. Yep, there it is. Now, they did them opposite of what they said here. This is Fahrenheit to Celsius. You're starting with Fahrenheit here. Well, you can't see that. Let me go back to black if I can. Okay. Yeah, I think you can see it now. If you're going from Fahrenheit to Celsius, you start at Fahrenheit, subtract your 32 from it, and then multiply 5 to 9. Why is that? For every 9 degrees Fahrenheit, you have 5 degrees Celsius. So you want the Fahrenheits to cancel out, and that gives you degrees Celsius, and that's where you get that one. Or you can, if you're doing it all at once, like making ice cream or something like that, you could measure the temperature that way. Okay, not that it would matter any. Okay, now Celsius to Fahrenheit, that's this one. Oops, I didn't change back to yellow. Okay, it would be 9 degrees Fahrenheit to every 5 degrees Celsius. So you want your degrees Celsius on top here so they can cancel out, leaving you degrees Fahrenheit. And you have to also add to that 32 degrees Fahrenheit to get you what your temperature scale is there. Now, is that someone trying to communicate to me, or is that just, I don't know what? And then the Celsius to Kelvin, that's correct here. Let me go back and do yellow again. Okay, if I can get the yellow to show up here. There we go. This is that one. Okay, if you know your Celsius and you're trying to get to Kelvin, add 273 to it. This would always have a degree symbol by it. This one does not. Okay, the Kelvin does not. Okay, any questions on your conversion factors? Okay, we'll be doing, in fact, I think the next example is doing that. Okay. And by the way, I had failed to mention, Fahrenheit was a very good physicist, not meaning to knock him there. He invented the mercury and glass thermometer with this scale based on arbitrary chosen reference points. So it wasn't just he picked that out of the blue. He was also a very, very good scientist. He developed that scale. And if you compare the dates on that, Fahrenheit was 1686 to 1736. So boy, he had a pretty long life there. That was no, it wasn't all that long, was it? 50 years. Whereas under Celsius, 1701. So he came along much later until 1744. So he only lived 33 years. So they didn't do too well back then. Okay. I don't know if they give us anything on Thompson. I think that will be later, if you're interested in following up with that. So let's do example 1. And I think I'll do it on this slide because it's here for you to see the things. The average human body temperature is 98.6. Let me see if I can get my pen to show up here. There it is. 98.6 degrees Fahrenheit. You can put this, oh, here's Dre. Okay, let me get Dre here. I don't think he's been here yet. So let me get them marked present. So bottom part of the alphabet, what's that again? Okay, I don't know if you know your microphone's on, but somebody's it is. Okay, so the middle part of the alphabet, 4 in a row. Bottom part of the alphabet, 3 in a row. Top part of the alphabet, 2 scattered out there. Okay, and then quite a few spaces there. So hopefully some more will be coming in. All right, so we know that normal average human body temperature is about 98.6 degrees Celsius, Fahrenheit. Okay, so what is the equivalent temperature on the Celsius scale? Okay, well then what we know we've got to do is drop this to how many degrees above freezing. So you would subtract 32 degrees Fahrenheit from that. Now that makes sense. You're subtracting Fahrenheit degrees from Fahrenheit degrees. That gives you degrees Fahrenheit, right? How many degrees Fahrenheit above your freezing point? Okay, so we're going to multiply that by blank 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 blank. Okay, these are your conversion factors. Put the units in their place first. I'm going to go back and change something now. I said blank blank, but really it's better just to use a single blank. Okay. Okay. You will put, well, it won't go back. Okay. Degrees Fahrenheit in the denominator here, degrees Celsius in the numerator here. Because this difference here is going to be degrees Fahrenheit, and you'll cancel out degrees Fahrenheit here. So let's go on and do this difference. Okay, you can put an extra 0.0 there if you want to, and that'd be 6.6. Any of you who are superstitious, that's 6.66 degrees Fahrenheit. Okay, so these are going to cancel out then. Oh, let's match the numbers with the units. We knew that we have 9 Fahrenheit degrees for every 5 Celsius degree. Okay, so I'm going to, because my calculator was acting up today, I'm going to do 3 will go into 9 3 times, and 3 will go into 6 22.2 times. And then I know 3 will go into 22.2. 3 will go into 21 7 times, and 3 will go into 12 4 times. So that's 7.4. Okay, so take the 7.4, multiply it times 5. You can do this on your calculator and it's a lot easier. Okay, and that's if you have 20, carry a 2, and this would be 37 degrees Celsius. So if you were visiting a doctor in England, Canada, or somewhere else, and they took your temperature and it was 37 degrees, don't think you're dying. That's normal temperature on the Fahrenheit, on the Celsius scale. If you're 40, you got a big temperature. If you're 35, you're chilled. You're really chilled, and you need to warm up. This being very anemic, I'm finding sometimes my hands are just freezing, and they never used to be that way. My wife said, "How are your hands always warm?" Well, I had better circulation or something then. What is anemia is just driving me nuts. So that's what they've got in the book, 37.0. Well, they just round it to 37 degrees Celsius. Okay. Example 4.2. The bank's thermometer display, maybe you're driving in Canada or Mexico or somewhere, and it indicates 20 degrees which happens to be near room temperature. What is the equivalent temperature on the Fahrenheit scale? Now I don't know what it is outside now, but when I went out to eat lunch, my dog and I went out together, it was pretty close to probably 20 degrees Fahrenheit. I mean Celsius. Okay, so let me clear this screen if I can find, there it is. Okay. For some reason, my pen isn't showing up again. This just drives me nuts. Okay. There we go. Okay. I'm going to try it again. No. Why it's doing this, I don't know. Okay. Well, I'll tell you what I'm going to do. Okay, there, I finally got to see it. Okay. And let's erase all the ink. Erase all the ink. There we go. Finally got it. Okay. So it says here a bank thermometer or temperature display indicates 20 degrees Celsius. And they tell us in parentheses that's about room temperature. Okay. Now what we have to do is do your blank blank here. Okay. These are for numbers. That is for your units. Okay. Your units, you're going to want degrees Celsius in the denominator, degrees Fahrenheit in the numerator. So those can cancel out. Okay. And this will give you how many Fahrenheit degrees you are above the freezing point. Okay. Well, what's that ratio? Good old Dolly Parton. That's a 9 degrees Fahrenheit to every 5 degrees Celsius. Okay. Well, I can do this. 5 will go into 20 4 times. 4 times 9 is 36 degrees Fahrenheit above the freezing point. What is the freezing point? 32 degrees Fahrenheit. Only add similar degrees. That gives you 68 degrees Fahrenheit. That's pretty close to room temperature. I wouldn't be at all surprised that the room I'm in right now is very close to 68 degrees. When we went out at lunch, I think it was closer to 70, okay, Fahrenheit outside. It's probably dropped off some now. Okay. Now, oh, here's William Thompson. He was 1824 to 1907. And so you see his scales came about generations after the other two. The other two lived about the same time. He lived, it would be 76 plus 7, 83 years. So he lived quite a long time. Okay. All right. Now, next we'll go to example 4.3. A science article refers to a temperature of 300 Kelvin. Okay, so there we have a scale 300.0 Kelvin. Notice you don't use a degree symbol with that. Okay, what is the equivalent Celsius degree? Well, what's your formula there? Whatever Kelvin you have, subtract 273 from it, and that, whoa, here's Brianna. Let me let her in and mark her present. All right, Brianna's here. All right, filling in a little bit of the gap there in the middle part of the alphabet. Okay, still the top part is pretty sparse. Okay, so hopefully we'll get more in. Now, let me make sure we got enough. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Finally broke double digits. Let's make sure we did. Yep. And let me make sure I've got everybody here that I hope to see here. I hope more will be coming in. All right. I'm going to minimize that back down. Okay. So, what would be the Celsius temperature then? I think that's what it was asking. What is the equivalent Celsius temperature? Where is my pen? It's backwards, no wonder it is. That would be right around 27. I'll just leave it 27 degrees Celsius. I don't see how they can get any more digits than that. Okay, 27 degrees Celsius. All right, the next question it asked was, what is the equivalent Fahrenheit temperature? Wait a minute. Did we have a formula that takes you from Kelvin to Fahrenheit? Not directly. Okay. Now this is a sort of a dumb example, but not that I like shooting elephants or anything. But if you were an elephant hunter and you were out there trying to shoot a blue elephant, what kind of gun would you need? A blue elephant gun, right? Of course, okay. But what if you wanted to shoot a red elephant? Do you have to buy a new gun? No, you swing him about him by his trunk until he turns blue and then use your blue elephant gun. Makes sense, right? Well, same thing here. Don't come up with a new formula. Go from Kelvin to Celsius and then go from Celsius to Fahrenheit. We already know how to do that. Okay, so 27 degrees Celsius, you're going to have to multiply that by blank blank to get to degrees Fahrenheit above freezing. Okay, number of degrees Fahrenheit above freezing. So you're going to need to have your degrees Fahrenheit here, degrees Celsius down here, and you know that ratio. Good old Dolly Parton, 9 to 5. Okay, 9 degrees Celsius is the same as 5 degrees Celsius. Okay, now this isn't going to be as easy to do in my head, so I'm going to have to hope the calculator works then. But this gives you how many Fahrenheit degrees above freezing you are, and then you take that, add to that 32 degrees Fahrenheit, and that gives you your actual temperature in Fahrenheit. And by the way, 27 degrees Celsius is well above room temperature. Remember, 20 degrees Celsius is room temperature, so this should be something greater. Now, earlier today, my calculator would not come on, but it's now doing okay. So we'll do 27 times 9 divided by 5, and then add to that 32. And that gets us right up there around 81 degrees Fahrenheit. And remember, if room temperature was around 68 to 70, 81 degrees is a good amount above room temperature. Not going to have many of those degrees days left this year. Okay, it'd be nice if we did, but I think those days are past. I need to plug in my phone because we do have a lab coming up today. I want to make sure we've got that covered. Okay, and in your book you'll see the B part there was 81 degrees Fahrenheit. It was, I think, 80.6. They rounded to 81. All right, now if you turn to page 94 in the big book, which is 4-8 in the smaller book, they have at the top of the page a little blurb on goosebumps and shivering, which is sort of an interesting kind of a concept. It's a nice little read. It's not trivial, but it's a nice little read. And basically, when you get cold and start shivering, what your body is doing is moving the muscles really quickly, trying to heat your system up. Okay? Now, why the goosebumps? Okay? Or I've heard some people call it, oh goodness, what's the other name for it? Chicken flesh or something like that. It's another bird type term. What it's doing is trying to contract to reduce the exposure that you have to chill off anymore. Okay, well worth a read there. Read up on that. So there's our temperature scales. Let's move on to, and there's your conversions again. I already had those listed, hadn't I? Yeah. Let me clear my screen here so you can read them a little bit better. Okay, those are your formulas. You don't have to memorize them if you don't want to. You can just use them. Look them up when you need to. Remember, you convert the Celsius degrees to Fahrenheit degrees, then add 32 to it. When you're going the other way, subtract the 32 from the Fahrenheit before you convert Fahrenheit to Celsius. Here it's a 9 to 5 because you 9 degrees Celsius for every, no, they've got that backwards. 9 degrees Fahrenheit for every 5 degrees Celsius, and that way the degrees Celsius will cancel out here, giving you Fahrenheit. Remember, this is also Fahrenheit here. And here you subtract Fahrenheit from Fahrenheit to give you how many degrees Fahrenheit you are above freezing, and then 5 degrees Celsius for every 9 degrees Fahrenheit. The Fahrenheits cancel out. You got it. For Kelvin, it's not degrees anymore, just Kelvin. Your degrees Celsius plus 273 gives you K. Not degrees K, K. Okay. Now let's talk about heat. This is section 4.3. What is heat? Now you'll hear several different similar definitions to it. Here's a good one. It's a form of energy transfer between two objects. It's not energy itself, though it kinda is. It's a form of energy transfer between two objects. Okay? Now, let's say I'm happening to be feeling my neck right now. My neck feels quite warm compared to the temperature of my hands. So my neck is transferring energy from it to my hands, which is warming up my hands. I don't know why my hands are so cold, but ever since I've had this anemia, they just seem to be cold. Okay, so that's heat, a form of energy transfer between two objects. Okay, now let's think about energy. You have external energy, which is the total potential and kinetic energy of an everyday sized object. Okay? Now, if you think of it in those ways, you think that's mechanical energy. External energy is mechanical energy, total potential and kinetic energy of an everyday sized object. So that's what you're starting with. Now, that's external energy. Internal energy is the total kinetic energy of the molecules in that object. Okay? Remember, that's how we define temperature. Temperature is related to, proportional to the total kinetic energy of the molecules in the object. That's what temperature is related to. Now, the external energy can be transferred to internal, resulting in a temperature change. Okay? So external energy is total potential and kinetic energy of an everyday sized object. Let's just take your hands for instance. Okay? If you take your hands together, mine not nearly as cold as they were a while ago, move them together, everyday sized object, and then let's also rub them together. Pushing them together while you rub, what do you notice? They warm up. Okay, try it, do it. Push them together and rub. You can feel them getting warmer. Okay, why is that? You're taking external energy, that kinetic energy of rubbing your hands together while you're pushing too, there's a little bit of potential there too, and you're increasing the temperature of your hand. The external energy can be transferred to internal, resulting in a temperature change. Okay, so that's the first introduction to heat. We're going to come back and give a couple more definitions later. Okay, now here's an example. Here's a gal pushing on a table and trying to push it across the floor. Now she's making a little bit of a mistake there because she's pushing down on the table while she's pushing it across the floor. When she's pushing down on the table, she's making more friction down here between the table feet and the floor. And so when she does that, she's actually increasing the vibrations of the thing. So if you had really sensitive thermocouples down here, that's another way of measuring heat, a thermocouple. You could tell that indeed the temperature is going up very slightly, but it is going up. Her external energy is increasing the internal energy of those molecules between the feet and the floor. Okay, that is one form of increasing the kinetic energy of the molecules in the feet and the floor by adding some external energy to the system. Okay, now I think I asked this question early on, is heat the same as temperature? And the answer is no. They're related, but they're not the same. Temperature is a measure of the hotness or coldness of an object. Okay? It is based on the average molecular kinetic energy of that object. Okay? The total average molecular kinetic energy of that object. That's what temperature is. Heat, on the other hand, is based on the total internal energy of the molecules. Total internal energy. Not just the average kinetic energy, the total internal energy of the molecules. Now, if you, okay, I'm going to put up the slide first. If you had a mug of coffee here, perhaps really hot coffee, or you had this nice little dainty cup of coffee. This was 250 milliliters. That's a full liter. So you have 4 times the amount of coffee here as you do there. But let's say that coffee, both of those coffees, are at 90 degrees Celsius. Now that's pretty close to boiling point of coffee. So this is almost like that McDonald's coffee that's so hot you can burn yourself on it. Okay, maybe not quite that hot, but it is. Well, guess what? You got 4 times the amount of coffee, you're going to need 4 times as much ice to cool that coffee as, or they're calling it water, okay, as it did this quarter of a liter, okay, 250 milliliters. Because there's more heat, because there's more substance here. They're at the same temperature, 90 degrees, but it takes 4 times as much ice to cool this as it does that, because there's 4 times the volume of this as there is that. Okay? Now, another way to look at it is, this is a really gross exaggeration. Let's say you had a bathtub full of water, but it's warm water. Okay? Not hot water, but warm water. You also had a thimble. I don't know if any of you have watched your mom or grandmother sew or something. They put that little metal thing on the finger so they can push the needle through and not stick them in the fingers. That's called the thimble. Let's say you had that little bitty thimble. You filled it up with water, which not much, very much water at all, but heated it up almost to boiling. Okay? But that bathtub sitting there with just pretty warm water, okay, nothing anywhere close to boiling, which has the most energy? That bathtub. Just a little flick of ice in that thimble and it's going to drop the temperature like crazy. Put a little sliver of ice in the bathtub, you won't even notice it. Okay, again, it depends on how much water you have. Okay, temperature and heat are not the same. They're related to each other, but they're not the same. The heat is based on the total internal energy of the molecules. Doubling the amount at the same temperature doubles the heat. Now, I don't like the way they phrase that, but it is correct. Doubling the amount of, say water or whatever you're dealing with, doubles the amount of heat, even though you're at the same temperature. Okay, I'm going to have to get something else. This is okay. Here's another definition of heat. I told you they're going to give you several of them. Heat is, and by the way, This is somewhere around page 95, top of 96. Heat is a measure of the internal energy that has been either absorbed or transferred from another object. So that goes back to the same definition we had back here, that heat is a form of energy transferred between two objects. Okay, so here's another way of expressing that: a measure of the internal energy that has been either absorbed or transferred from another object. Okay, now two related processes here. If it's being absorbed from another object, then you're heating up the second object, okay, increasing the internal energy of the second object. If, however, it's being transferred from an object to another object, that is then cooling. That's decreasing the internal energy of the object, okay? Now, how do we go about doing that? Our heating methods, number one, is by a temperature difference, okay? So let's just say that I take some tap water and put in the teapot and turn it on. Now the temperature difference, energy always moves from the higher temperature regions to the lower temperature region. I put that water in there, turn on the teapot. We have one that has a little button on it, and you hear it start making noise. That's heating up. Always moves from high temperature to low temperature. Okay, now there is another way that you heat, and this is energy form conversion. That's transfer of heat by doing work. That would be like rubbing your hands together. Okay, there is a temperature difference there, but it's not like I'm putting a glove on the hand to increase the temperature. I'm rubbing them together. Okay, that's an energy form conversion, transfer of heat by doing work on the hand. So two different ways that you could do it. Now, how do we measure heat? Now this is on page 96 or 4-10, the measures of heat. Now, here's a little bit of a problem, folks. People never really understood heat very well. If you go back to the time of Aristotle, he said there were 4 elements in nature: earth, wind, fire, and water. Okay, 4 elements of matter: earth, wind, fire, and water. 3 of those used to make up a singing group. I don't know if you remember them: earth, wind, and fire. Okay, forget that. Okay, so there's some problems with that, though. Obviously, there's more materials than that. But based on Aristotle, because he said it and everybody believed it and everybody bought it hook, line, and sinker, what they thought after a while, they said, hey, earth materials is cheap, air is cheap, water is cheap, and fire is not that bad. So if we can manipulate those 4 elements, we can get gold, we can get platinum, we can get silver, we can do, if that's all that there is, those 4 elements, then we should be able to make something very, very expensive out of things that are very, very cheap. And we can make a mint on this, okay? And that's when the early chemists called alchemists started fiddling around with things and trying to come up with ways to get a cheap buck. Okay, in other words, take very cheap materials, earth, wind, water, and fire, and make out of that something that's very, very expensive and valuable. So boy, we can go here. Well, earth is made up of all different kinds of materials. Okay, compounds, elements, all kinds of stuff. Wind, again, a mixture of all kinds of gases. Okay, water, a compound, not an element at all, and it's made out of hydrogen and oxygen, but chemically combined. And then fire isn't even a material, so it can't be an element. But for many years, they counted it as what they call it, an ethereal substance. You can't really measure it, but it has to be in there. Now here's what they base that on. Back then, most of the fire that you had was wood-based. And they knew that that tree grew somehow, making that wood, and then you chopped the tree down, split it up, did whatever you wanted it to it, and lit it off, and you get smoke coming out of it, you get heat coming out of it, you get all sorts of things, and you're left with a very, very light, fine ash. And that's all that's left. So they thought heat had to be some sort of ethereal substance that lived somehow in that wood. Okay? Now, we'll talk about a guy a little bit later who disproved that, but that's what it was. So for many years, even when we came out with the metric system, they still counted heat as an element. And one of the early periodic tables, before they had the best one, had caloric as an element. Well, they took that name that they used for heat, and that is a metric unit for heat, calorie. Now, how do they define that? It's the energy needed to raise 1 gram. Now, 1 gram is a tiny amount of matter, okay, of mass. It would be like maybe an aspirin tablet, okay, very small, to raise 1 gram of water 1 degree Celsius. Now, how big is a gram of water? Think of your little fingernail here. Okay, that is about 1 centimeter across. Okay, do it again like this and like that. You have 1 cubic centimeter. Here, here, and here. Okay, that's a tiny little, tiny little block of water. To raise that 1 gram of water 1 degree Celsius, that doesn't take a lot of heat. But that's what they call a calorie. Now, remember, this is metric units. That's such a tiny amount of heat. After a while, they said they were having to go to kilocalories, meaning thousands of those calories. Well, the people, especially that dealt with foodstuffs and things like this, didn't like having to write kilocalories all the time. So what they did, they rewrote it as capital C calories. So if any of you happen to have some food stuff or water stuff or liquid or something else, I'm going to see if I can get this Coke can out of the koozie or whatever you call these things without spilling something all over myself. And it's not doing a good job of this. I'm going to make a mess here. There we go. I got it. Okay. I look at this Coke, and what it says here, that 1 can of Coke has 140 calories. But if you look at that, I don't know if you can read it because of the glare, that's a capital C calorie. That is kilocalories, thousands of these calories. 140 kilocalories, 140 calories. So if you're looking at something and say, oh, that's not a lot of calories, that little c calories, that's thousands of them. Okay. So a kilocalorie would be the amount of energy needed to raise the temperature of 1 kilogram of water. What's a kilogram of water? A kilogram of water would be 10, let me make sure I've got this right, 10 centimeters by 10 centimeters by 10 centimeters. That would be the size of a block of water. That's 1 kilogram. Okay, the amount of heat required to raise that chunk of water 1 degree Celsius. Okay, now in the old English system, okay, not many people use this anymore, but a few people do. They used the British thermal unit English, British thing, saying a BTU. Now, back when I was younger, that's what most air conditioning systems were measured in, as BTUs, British thermal units. That's the energy needed to raise the temperature of 1 pound of water. Now, 1 pound of water is way bigger than 1 gram of water. A little bit less than 1 kilogram of water, but way bigger than 1 gram of water. Okay, to raise 1 pound of water, 1 degree Fahrenheit. Remember, a degree Fahrenheit is about half the size, a little bit more than half the size of a degree Celsius. So it's raising it a smaller amount, but a pound of water is way, 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 way bigger than a gram of water. So a kilocalorie is a little bit more than a BTU. A BTU is way more than a calorie. Okay. Now, we'll be talking about them shortly, but the mechanical equivalence of heat is 4.184 joules of energy is the same as 1 calorie of heat. Now that's a little c calorie. Now that means a joule is an awfully small amount of energy, okay? Because it takes 4 of them to make 1 calorie. 1 calorie is a very small amount of heat too. So that's called the mechanical equivalence of heat. In other words, remember, they thought heat was an element, whereas they thought energy was something completely different. So they had joule to measure energy, calories to measure this ethereal material called heat. They found out that's just the same form. Okay, so 4.184 joules makes 1 calorie. 4.184 kilojoules makes 1 capital C calorie or kilocalorie. Okay, so those are good numbers to remember or write down and use when you need them. All right, now before we get to specific heat, let's do example 4.4. This is on page 96 or 4-10. Okay, let me see if I can get enough space. Yeah, let's do it right here. All right. A 1,000 gram car. Am I still in yellow? I think I am. So this will be 1,000, and boy is this ever precise, 0.0 kilogram car. Okay, this is a mass, for some reason it's not writing, mass of the car. I want that out of there. Okay, mass of the car, that's what kilogram measure. Moving at 90 kilometers per hour. So 90.0 kilometers per hour, and they give you the equivalent of that. That is 25.0 meters per second. I like that better. This is a measure of the velocity of the car. So there's the mass of the car, there's the velocity of the car. We're going to use this one, not that one. Okay? How many kilocalories are generated when the car brakes to a stop? Time out for a moment here. Does anyone know what's really happening when you press on the brakes in a car to make the car stop? What you're doing, the brake drum and the brake pads are being pressed together just like your hands being pressed together, and they produce an awful lot of heat. Okay, an awful lot of heat. Okay, if you've ever messed around with a car changing the brake pads or the brake shoes or however you want it, the disc, whatever you want to call it, you don't do it when it's just come into the shop. You let those things cool off some because they are incredibly hot. Okay, so that's what we're dealing with now. This car moving at a really high rate of speed, 90 kilometers per hour, which is about 20 meters per second, and it's a mass of 1,000 kilograms, which isn't all that big. It's sort of a small car. A lot of cars are closer to 2,000 kilograms, but so it's sort of a small car moving at a high rate of speed. How many kilocalories are generated when the car brakes to a stop? So this is the initial, where is my pen? Okay, this is the initial speed. Final speed is 0 because it comes to a stop. So how much kinetic energy is lost there? The kinetic energy that's lost is 1/2 mv squared, which would be 1/2 1,000 kilograms times 25.0 meters per second squared. Okay, now that's going to come out to be a big number. Okay, I'm going to first take half of 1,000, make it 500. And just because I don't really want to do that in my head, but I think I can, 25 squared is 625, I believe. Okay, and that would be meters squared per second squared times 500 kilograms. I shouldn't have crossed out the kilograms too. Okay, and this would be something on the order of 3,000 I think it's a 125. I think that's about what it is. Yeah, 312,500 joules. But remember, a joule is a very, very, very small unit. So if you wanted something a little bit bigger unit, smaller number, you could say 312.5 kilojoules, 1,000 joules. Move the decimal 3 places to the right. Okay, so that's how many joules. But it didn't ask for joules. How many kilocalories are generated when the car brakes to a stop? Well, they just gave us that a little bit ago. They said that just up on the upper part of the page, 4.184 joules is equivalent to 1 calorie. Okay, we have kilojoules here. I want to flip those over then. So we have 312.5 kilojoules, and that would be multiplied by blank over blank, and we want the kilojoules in the bottom and kilocalories on top, and that would be 4.184 kilojoules, because you got kilo in front of both of them, is 1 kilocalorie. Okay, now this is pretty amazing, but let's hit it. Okay, get to my calculator, and it says here 312.5. By the way, the kilojoules are going to cancel out here and here, and that gives you, and divide that by 4.184. That's how many kilojoules are in 1 kilocalorie. Okay, 74, I don't know if you can read it, 74 point blah blah 69, almost 75 calories, capital C calories. Uh-oh, how much was that can of Coke, how many calories was that? Kilocalories, capital C calories. Wasn't it around 120? That means I would have to be able to stop a 1,000 kilogram car. Actually, I said that wrong. That's about a normal size car. I was thinking a 1-ton car, but that's 1,000 kilograms. Okay, I would have to stop a 1 kilogram car going about 90 kilometers per hour, which is right around, I think, 50 or 60 miles per hour. That's what I would need to do to burn up that less than what that 1 can of Coke. That's pretty scary, isn't it? Okay. It's amazing how much energy, wasted energy, there are in soft drinks. Okay. Now, let's move back to where we were. Okay, there's that mechanical equivalence of heat again. 4.184 joules is 1 calorie, or 4.184 kilojoules is 1 kilocalorie, or capital C calorie. All right, that was what we had, 74.7. I didn't think to look at it. I just rounded to about 75 kilocalories. Okay, now let's move to specific heat. Okay, we've got about 40. Oh, here's iPhone coming back in. If I'm not mistaken, that was Jacob, right? Nope, not Jacob. Jacob was here. Who was that? Leon. No, Leon wasn't here, was he? Who is iPhone?
That was Thomas again.
Ah, that's it. That was Thomas. You got it. Okay, welcome back. Okay. Now, let's move on to specific heat. Now, there are several variables involved in heating something. Okay? And I'm going, okay, somebody, I, I believe you're getting feedback from my talking into your iPhone, so you might want to mute your iPhone. Thomas. Okay, good deal. Nope, not quite. All right, yeah, there you got it. Okay, now specific heat. I went to a physics conference, local Alabama conference, several years ago, and someone had brought a nice little get-up. Okay, and what that consisted of, they had a circular piece of metal. Okay, that they laid flat like this. Okay, circular piece of metal. It was probably about that thick. Okay, and all around it they had holes drilled. I'm guessing about 6 or 8 holes drilled. And they had pegs that fit into those holes in really nicely, tightly. Okay? Now, but those pegs were made out of different materials. Okay? You could tell it. You could look at that and tell they were different materials. Okay? I remember at least one was aluminum, at least one was iron, at least one was copper, at least one was brass maybe. They were all different materials. Now, they also brought with them a Bunsen burner. Remember, we saw that in the, well, why won't this advance or retreat? Okay. There, that's a Bunsen burner. It's a flame. They hooked it up and propane or something like this, and it produces heat. It burns. It's a really hot flame, blue flame. Okay. Now, so they had this Bunsen burner over underneath this plate, and each one of us had a peg. We were holding the peg. They were room temperature, no problem there, and we pushed them into the hole that was closest to us, and we saw who could hang on the longest. Well, guess what? Whoever had that, I'm believing it was aluminum, soon let go. Okay? No, I'm sorry, I said it the wrong way. We'll see in a minute. Okay? Different people let go at different times. Is that because we were different levels of wimpiness? No. because you have a temperature change anytime you're heating something. Also, you have mass. Remember, we talked about the thimbleful of water as opposed to a bathtub of water. Okay, that enters the picture here. But we also have different types of material. Like I said, some of those pegs were aluminum, some were iron, some were copper, some were different materials. Okay, different materials require different amounts of heat to produce the same temperature change. What that measures is your specific heat. This is summarized in one equation, and here it is. Q now in this chapter, capital Q is going to stand for heat. Okay? And heat is equal to M, the mass, we talked about that, different amounts of mass, times C is specific heat. And then the delta T, that's your temperature change. Remember the delta, I've been focusing on that a lot. Finally, the book focuses on it, delta T. That is our basic heat equation. Q is equal to MC delta T. Now here's that block of aluminum. This is not a peg, but this is a block, about 10 grams of aluminum. If it's at 20 degrees Celsius, okay, and you put a Bunsen burner under it and add heat to it, it will absorb 176 calories of heat, and because its specific heat is 0.22 calories per gram per degree Celsius, that will raise that to 100 degrees Celsius. Or if you cooled it, it would take 176 calories released from that to drop it from 100 degrees Celsius, which would be hot enough to boil water. That would burn your hand down to room temperature at 20 degrees. So that's a measure of the specific heat of aluminum. If you had 10 grams of copper, 10 grams of copper, because copper is a lot denser than aluminum, is going to be a lot less. And guess what? That only requires 74.4 calories to be absorbed or released, one way or the other, to change the temperature, that 80 degrees delta T. Okay? Much less. So whoever had the copper thing, he let go of it, or he or she let go of it a lot sooner than the person who had aluminum, because aluminum has a higher specific heat than copper by a long shot. Okay? Now, we didn't have any that were gold, but if we had them that was gold, 10 grams of gold is really small because gold is very dense. It's only 24 calories, and that specific heat is 0.03 calories per gram degree Celsius, whereas copper 0.09, 3 times as much, and aluminum is basically more than twice the specific heat of copper, almost 10 times specific heat of gold, about 7 times. Okay, so that relates to how much heat it takes a given material, to change its temperature. Specific heat. Okay. Now, they move into heat flow pretty quickly. Let's do the example that we have there before we get into heat flow. Okay, so I'm going to clear that out of the way, and we will do the example. This is example 4.5, and we'll do 4.6 as well. Okay, how much heat? So what we're looking for here is our Q. Remember, that's what heat is. Q. That's what we're looking for. How much heat must be supplied to a 500 gram pan? So 500 gram is a measure of mass. That's equal to 500, and it's at 0.0, yes, 0.0 gram pan. Okay, to raise the temperature from 20 degrees Celsius, so this is initial temperature, is 20 degrees Celsius, which is basically room temperature, to the final temperature of 100 degrees Celsius. In other words, you're going to boil water in that pan. Okay, that's the boiling point of water. Okay, if the pan is made of A, iron, B, aluminum, now they kind of cheated on you a little bit here. Okay, now what you need to do is go to the table on the next page, on page 98 or 4-12, and that's where you find your listing of specific heats. Okay, and let's just take a look at those. I don't know if you can read them from there. Hopefully you got your book so you can do them, but I'm going to read through part of this list. You may find some things surprising here. Air has a fairly low specific heat, 0.17 calories per gram degree Celsius. Aluminum, 0.22. So aluminum takes more heat to raise aluminum 1 degree than it does an equal mass of air. Of course, air has very low mass. Okay, concrete's about 0.17. That's about the same specific heat of air, but of course a gram of air, it takes up a lot more space than a gram of concrete. Copper, 0.093. We saw that on that previous graphic. Glass on average is about 0.16, about like concrete. So when we were in the classroom, your specific heat of glass and concrete blocks were about the same. Okay, gold, really slow, 0.03. That's what we had before. Ice, believe it or not, has one of the highest specific heats of anything listed in the table so far, 0.5. Okay, iron, 0.11. There's iron right here, so let's go on and write that down while we've got it here. The specific heat of iron, C for iron, is 0.11 calorie per gram degree Celsius. That's your change of temperature. Okay, let's go on down. Lead. Lead is actually almost as low as gold. Gold was 0.03, lead is 0.0305. Mercury, just a little bit higher than that, 0.033. Seawater, believe it or not, is way up there at 0.93. Silver, 0.056. So that's down there, not quite as low as gold, but getting close to it. Soil on average is about 0.2. Okay. Steam, 0.80. My phone keeps ringing downstairs. I don't know what it is. The politics is over with. I don't know, but I'll go check it out in about 25 minutes or so. Okay, water. Water has one of the highest specific heats of any substance on the planet. It takes 1 calorie, 1 calorie of heat to raise 1 gram of water 1 degree Celsius. It takes a fraction of that for just about anything else. Of course, ice is frozen water, so it's about half that. Seawater is awfully much water, so that's about 0.93. Steam, in fact, they don't list that here, 0.48. Okay, it's just really amazing. Oh, they do list it there. It's 0.48. So water is one of the highest specific heats, and we'll talk about that a little bit later. Oh, I didn't write down aluminum. Aluminum was 0.22. So the specific heat for aluminum, C for aluminum is 0.22 calories per gram degree Celsius. Okay. Now, okay, so how much heat is required? Well, remember our formula for heat? It's been a while now. It's Cm delta T. Okay. Well, we got to figure out what the delta T is. We know what the C's are down here. We know what the M is here. Both of those have the same masses. But your delta T, that change of temperature is delta T is 80.0 degrees Celsius. Okay, so your C here, which should it ask for first? Iron. That would be 0.11 calories per gram degree Celsius. Multiply that by your mass, and the mass was 500 grams. And multiply that by your delta T, which was 80.0 degrees Celsius. Okay, notice what happened. This grams and that grams cancel out. This degree Celsius, that degree Celsius cancels out, and that gives you calories. That's a good thing to measure heat with, is calories. So let me get, where's my calculator? There it is. Okay. My phone is not charging very fast today. Okay. So that's 0.11 times 500 times 80 equal 4,400 calories. Okay, what do I do with my pen? The Q for iron the amount of heat it takes to heat that iron 80 degrees, 500 grams of that iron, 80 degrees was 4,400 calories, and those are little c calories. Okay, or if you wanted to use kilocalories, that's 4.4 kilocalories. Yuck! This thing is so aggravating. Okay, 4.4 kilocalories. Okay, well, let's do the same for aluminum. Q for aluminum would be, its specific heat is 0.22 calories per gram degree Celsius times 500, same mass of aluminum. Now 500 grams of aluminum is the same mass as 500 grams of iron, but you don't need nearly as much iron to make 500 grams as you do aluminum, because iron is much denser. Okay, I'm running out of room here, and your 80 degrees was still your delta T. And again, the grams cancel out grams, the degree Celsius cancels out degree Celsius, and that leaves you with 0.22 times 500 times 80, and that gave you 8,800, or exactly twice calories. And again, if you don't like to use such big numbers and you want to go to a smaller number, a bigger unit, that would be 8.8 kilocalories. Okay, now they probably are going to use 3 significant digits, so I would probably put an extra 0 there and an extra 0 there. Okay, I don't know that they do that, but let's see. All right, that was example 4.5. No, they just leave it as 4.4 kilocalories for iron and 8.8 kilocalories for aluminum. Okay, now what does that mean? If you have an iron pot, the odds are it's going to take less time for you to heat that up than an aluminum pot. Okay, now they need to be about the same mass for that to be true, but I think you'll find that the case. And that's why a lot of the good old cooks like to use the cast iron skillets, because they could heat things up, get that chicken frying a lot faster. Okay, and I was all in favor. Okay, so there's 4.5. Let's go to example 4.6. Okay, so I'm going to clear the screen. Does anyone need the screen a little bit longer? Okay, 4.6. What is the specific heat? Okay. Okay. I'm going to plug back in my phone because it's not charging very fast today for some reason. Okay. Okay. Now, 4.6 says, what is the specific heat? So in this case, we're looking for C is the unknown here. That's the unknown here. What is the specific heat of a 2 kilogram metal sample? So that's 2 kilogram is a measure of mass. 2 kilogram metal sample. If 1.2 kilocalories, that's a unit of heat. So your Q is 1.2 kilocalories. Okay, is needed to increase the temperature from, so your initial temperature is 20 degrees Celsius, room temperature again, up to 40 degrees Celsius. So that's not a huge increase, but some increase. Final is going to be 40 degrees Celsius. So you're not going close to boiling point of water yet, just heating it up some. Okay, now remember our formula that Q was equal to MC delta T. We're looking for C now, so let's divide away the mass and divide away delta T. So if we divide both of those here, mass and delta T here, okay, these go away, these go away, so your C, that's what we're looking for here, is equal to Q divided by M delta T. Okay, well, what was our Q? 1.2 kilocalories divided by mass, 2 kilograms. And your delta T here, that's 20 degrees. Goes from 20 to 40. That's a change of temperature of 20 degrees Celsius. So we'll put 20 degrees Celsius here. Okay. Pull out my handy dandy calculator again. Didn't get too much of a charge on it, did I? Okay, so we do 1.2 divided by 2, and then divide that by 20. Hit equal, and what do you have? Oh boy, I'm going to run to the bank. That's about 0.03. Okay, now they're using kilocalories here. You could use calories or it's kilocalories, either one. Kilocalories per kilogram degrees Celsius. Now, look at this. 2 kilograms of that material. And what material has a specific heat of 0.03. Anyone got your table in hand? Look that up. If everything's right there, that would be 2 kilograms of gold. If you had 2 kilograms of gold, I'm heading for the bank right now, okay? Because I am now a wealthy man, okay? Because if gold is selling for, oh, I don't know, what is it now, about $400 or $500 an ounce, and an ounce is a 16th of a pound, and a pound is, it takes 2.2 pounds to make a kilogram. My word, I'm a wealthy man, okay? So head to the bank if you had that much gold. All right, there's a nice little concept there, concepts applied on more kitchen physics. I don't remember when the first kitchen physics was, but consider the following information as it relates to metals of cooking pots and pans. It's easier to change the temperature of metals with low specific heats. That's what we remember. The last one was that you had iron and aluminum. Iron had a much lower specific heat, so it was a lot easier to heat food fast than iron. It is harder to change the temperature of metals with high specific heat, like aluminum. So it says, look at the list of metals in that table up there, table 4.2 that I showed you, and answer the following questions. Considering specific heat alone, which metal could be used for making practical pots and pans that are the most energy efficient to use? Well, certainly the lowest specific heat would be gold, but that's not practical, okay? After that would be mercury, okay? That's not lead. That's not practical, okay? Mostly because lead is a carcinogenic material. It can cause cancer. You don't want to cook in lead, okay? Because lead is also a soft metal, and just scraping on it, you could get lead into your food. No, not that. Mercury, absolutely ridiculous, because mercury is a liquid at most temperatures and pressure. We'll keep on going up. What's the next lowest specific heat? Copper, 0.093. So copper, and a lot of them, I don't know if you've seen it, these pans that have a copper bottom on it. You know, it's sort of a copper colored bottom, but silver on the top. That's because they're taking advantage of that low specific heat of copper. Okay? Now, again, considering specific heat alone, now this time we're not being practical, what would be combinations of metals provide any advantage for rapid temperature change? And it seems like that's the same question, okay? Copper. I left off one. Silver would not be practical. Silver was 0.056, less than copper. Very impractical, because it's very, very expensive. All right. That being said, there's your two examples using specific heat. Okay, let's move on to, there was your formula, and remember you can manipulate the formulas to calculate specific heat, mass, or change of temperature. So be ready to do that just like we did on that problem. All right, let's talk about heat flow now. Now that word itself, that phraseology, is a throwback to the old days when they thought that heat was an element, a specific material, okay? Guess what? It's not. But they talked about heat flowing as if it was a material. Now, it's not a bad concept. It's okay. But guess what? It's not a material, okay? So you just have to take that with a grain of salt. Let's see. Make sure okay. There's three mechanisms for heat transfer due to temperature difference. One of these is conduction, okay? One of these is convection, and one of these is radiation. Natural flow, and we've said this earlier in an earlier slide. Let's see if we can find it now. Here it is right there. Energy always moves from high temperature regions to low temperature regions. That's the natural flow of energy from high to low. Always is doing that. Everything you deal with goes from high potential to low potential. So natural flow is always from higher temperature regions to cooler ones. Okay? Now I can remember my dad saying in the summertime, close the door, you're letting the cold out. Well, in reality, what we were doing is letting the heat in, because always the natural flow is from high temperature to low cooler temperatures. Okay? Now, sure, you could be letting hot air in, you could be doing other things, but really the or cold air in, okay, or whichever, natural flow is always from high temperature region to cold. Now, we're going to look at each of these different forms of heat flows separately. I'm real tempted to say what the difference is now, but let's look at them separately. First is conduction. That is heat flowing, which really it doesn't flow, it's not a material, through matter. What's the mechanism here? Well, here's what it is. Remember we said that when something heats up, the molecules move faster. They have greater kinetic energy, meaning greater velocity. They're moving faster. They collide with more energy. They bump into other ones, giving you more pressure. The hotter atoms collide with the cooler ones, and they give, with those collisions, then the heat transfers down the material. Okay? Now, hint, direct physical contact is required. It cannot occur in a vacuum because there are no molecules in a vacuum. Okay. Now, when we're talking about this mechanism, we're basically talking about, remember back when we talked about the phases of matter? Solid phases conduct heat. Okay? Solids conduct heat. The others we're going to talk about will be convection. That's not solids, that's fluids, which could be either gases or liquids. Solids are mostly conduction, because the atoms are fixed in place, and when these speed up, they bump into this one, bump into that one, bump into that one. Here's the illustration of that. Here you put the Bunsen burner underneath the end of a tube, a metal tube, and that metal tube, then you'll see here's the temperature level at that end. There it is a little further down, a little further down. This one's probably close to room temperature down here. Okay? Why? Because the molecules here move faster, they bump into these, they move faster, that gives you a high temperature there, a little bit less temperature there, a little bit less here, a little bit less here. Given time enough, then that whole tube will reach the same temperature. But the transmission of increased kinetic energy, which is increased temperature, moves down the tube like that. Okay? Direct physical contact is required. You can't have just it happening in a vacuum. So guess what? That doesn't happen in space. Conduction does not happen in space. There's not enough molecules there. Now, let's think of some of the good conductors. They would include things like your metals. And you might say, why would metals conduct better than nonmetals? Because metals are made up of what we call, you have atoms there, for sure, but those atoms are surrounded by free electrons. And these free electrons are free to move up and down. Those electrons are in direct physical contact with one another. They move very rapidly down the tube. Now, are any of you still associated with your high schools and go to the playoffs and things like this? Are they happening now, or is the season over with? Anybody? Any of you still got teams in the playoffs? On most years, do any of you have teams in the playoffs? High school teams or things like that?
Yeah.
You have, okay. About this time of year, this is about when playoffs are happening, and it's getting pretty chilly. Back in September, you're usually not too concerned about this, but now it's pretty chilly out there. Now, some of the old stadia that back when I was in school, the old benches were usually made out of wood and kind of flimsy and stuff like this, but then they went in and built the nicer stadia and they had aluminum seats. But about this time of year, when it was time to go to the playoffs and it was getting pretty chilly outside, did most people want to go to those nice aluminum benches, or did they go to the old wooden benches? Absolutely. And here's why. Wood is a lousy conductor. Aluminum is a good conductor. Okay, so you set your tush down on that aluminum seat and there goes the heat down the seat. Okay, and it feels awfully cold out there, that seat. Whereas the wood, it's a really lousy conductor. So you set your seat down on that and suddenly it comes to your temperature much more quickly. So poor conductors are large molecules because they conduct really slowly. Good conductors are things like those free electrons that they conduct really quickly. So if this is a metal tube here, that's going to conduct that conduct that temperature real quickly down the tube. If this was a plastic tube, that's going to take forever for that to get warm on this end based on that end, because plastic are great big molecules. Styrofoam, great big molecules. Wool, kind of a big molecule. Now they're getting into some other issues here about conductions, and we'll talk about that a little bit later. But let's hang off on those. Your poor conductors are things like big molecules, and we'll go from there. Okay. Conduction is mostly solids. Okay. Here's what's happening at this end of the tube when the heat is going there. It makes the molecules really vibrate fast. Those a little bit further down, they haven't started vibrating much at all. But that vibration moves down the tube, and that's why the temperature is hotter on this end, cooler, 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 because not all the atoms are moving as rapidly yet. That's what conduction is, and that's why it happens. Now, here are a few samples of your conductors. Okay, the very best conductor, and hang on to this concept for next chapter as well, the very best conductor is usually silver. Okay, next to that, and this isn't a fair display, the ones they listed here, the next would be iron. Water is a pretty lousy conductor of heat. Styrofoam is a terrible conductor of heat. Air itself is a really, really poor conductor of heat. And of course, a vacuum doesn't conduct at all because there's no molecules to bump into each other. Okay, so your metals are your best, silver being the very best. In your book, you'll see that copper is just behind silver. This is on page 99. Aluminum is close to half that of copper and silver. Iron then comes further down the list. Lead is a bit further down the list. Concrete's further down the list. Glass is further down the list. Tile is further down the list. Bricks are further down the list. Water, there's water showing up here. Wood that I mentioned, further down the list. Cotton, even further down the list. And styrofoam, here styrofoam was listed here. And glass wool, which is another type of insulating material, it's even further down the list. And air down here, and the vacuum, of course, is 0. Okay, so that takes us some of our sample conductivities. Okay, now before we hit that, let's talk about um, a little bit of that conduction. And here is a picture of somebody putting um, batt insulation in an attic that insulates better. That's basically somewhere around styrofoam or air. Now, it's probably not styrofoam or air, but air is involved with it. And what it does, what air is a poor conductor if you can get the air to be still. Okay? Now, think about this. I've got on a cotton shirt right now. It's not super warm. Over what I had this morning on was a flannel shirt. Now that's also made out of cotton. But the difference between the flannel shirt and this shirt is the flannel shirt has those little fibers. Flannel shirts, are a little bit puffier. Well, that puffy fibrous material actually traps air in between the fibers, which makes a much better insulator than this plain cotton shirt. This has a little bit of trapped air, but not very much. That's why wool is a warmer material, because wool has those fibers again. And anytime you can do that, this insulation in the attic, that's usually, I want to say it's either styrofoam or glass wool, or there's one more product, I can't think of the name of it now. But anyway, it's itchy stuff. It has lots of air trapped in pockets. Okay? I don't know if any of you are hunters or things like this and you go out in the cold temperatures to hunt and you wear long johns. Well, what long johns do, they trap the heat in those little gaps or spaces that air makes for a lousy conductor, good insulator. And some of you ladies, I don't know if you ever use the stockings that have, you would think the holes would be cooler than not holes, but in reality, those holes trap air and they actually are pretty warm. And same thing with wool socks and things like this. So we'll stop there and pick up next time with convection. So let me mark my page here on convection. And we've only got a little bit more in this chapter to go. I think we'll finish pretty soon next time. Actually, there's more than I thought. And then we'll move into chapter 6. So next week, we'll finish chapter 4 and move into chapter 6. Any questions? Okay, let's take a quick break. I've got to go down and see what all the phone messages were. I'm hoping my wife wasn't having trouble with cars. She would have called on my cell phone, I think. So anyway, I'm going to stop the sharing right now and stop the recording right now. Unless what I'm going to do is turn off the PowerPoint. We don't need that any longer. And shut this down. Nobody else waiting to get in. So, can't believe I'm so out of breath just walking upstairs. This anemia is driving me crazy. Okay. Let's go to, you can't see this, but I'm going to pull up the lab. You know where it is. I'll get to that in a minute. And I think we're lab 7 tonight, aren't we?
Yes, sir.
Okay. So I'm pulling it up now. And this is the pendulum lab, that's correct. And let's go to I can't get, okay, maybe I have to minimize this. I can't get it to open. Okay. Okay, that's not what I want. Okay, here's what I want. Actually, maybe not. Let me see. This may be quicker. Yeah, that's what I want. Okay, does everybody know how to get to the lab in Blackboard, or do you need me to walk you through that? Okay. Say again, show again. Okay, let's go to Blackboard. Okay, and I've got to scroll down to this course. Oh man, Blackboard is such a pain in the neck. I have to log in again. Okay, it's going to take me a few minutes because Blackboard is slow. Okay, and we want to get down to Physical Science 112. Okay. We're almost there. Okay. Okay. I think this is where I'll stop, go back to Zoom, and load this. Wait. I just got too many things open. Okay, here we go. All right, here's content. Okay, there was our announcement for today. And I'm going to move this. You can't see it, but I'm going to get it out of the way so I can see stuff. And let's see, do I need to move y'all? I think Valerie, you're in the way again, so let me move you up here. Okay, now you see where I am on Blackboard. Physical Science 112, that's this course, right? Y'all can see that? Okay, so we go down here to your weekly assignments and activities. Okay, now we're on, for the mini-term course, we're on week 4. Okay, so go to week 4, click on it, and it opens up down here. So I'm going to scroll down till you can see it. Now here was the overview and weekly to-do list. You can look at that if you want to, but instructional materials, that's where we are. So click on that, and now it opens here. So here's the labs. So here's the PHET, that Colorado, University of Colorado place that does the labs. Lab 6 is the one we did on Tuesday. We're doing Lab 7 today. And so since I'm here, well, that's where you go. And this is where you open up the PHET. So I'm going to open up the PHET here. I thought I already had it open. Let me see, Jacob, you're in the way again. Gonna have to move you again. Okay. No, I didn't open that. So I'll go on and open the PHET here. Just click on it and you're there. Okay. Now the other thing I'm going to do is go to Physical Science 112. I don't know why I've got 2 of them open. I think I'll close this one and do this one. Okay. Why in the world is that open? That makes no sense at all. Okay, I don't need that open here at all. Where was physical science? Let me go back to this again. There we go. Let's open that one. Ah, there we go. And we said lab 7, right? Yep. Okay, here's the pendulum lab. Okay. Oh, you can't see it yet. Let me get my screen share again and get this open. We'll be going back and forth between the lab here and directions here. So here's the directions. Go to Blackboard page for this course. We were just there. Go to course content. We were just there. Go to week 4. We were just there. Instructional materials. We were just there. Scroll down to lab simulation. That was that PHET thing. Okay. Click on simulations. That's where we were. So let's go to where in the world was it? I hope it's still here. Is it there? Yeah, there it is. Okay, so here we are at simulations. You can see that, right? Go down to physics, click on physics. Okay, now we're going down to pendulum lab. So it's alphabetical, so we got quite a ways to go here. There's balloons, there's build an atom, there's circuit construction, there's density, there's Faraday's experiment, there's gas, there's John voltage, there's lunar molecular motors. We're getting closer. There's optical pendulum lab. There it is. You see it? Okay, click on the pendulum lab. Okay, now what you need to do here is just click on the triangle in the circle. Got it? And there it takes, some of these take longer than others. Now, this will be doing the intro part. So let's click on intro, and this is what we got. Now I'm going to move some of you out of the way again, and this is going to be hard to see. Okay, so what we're going to do is click on stopwatch down here and period trace. We're going to need both of those in time, not quite yet. And this isn't working out well, so I think I'm going to move y'all way over to the left and see if that will work any better. Oh, it doesn't. Okay, there we do. Okay, now, nope, yuck. I don't know where to move y'all. Let me try you lower left, because wherever I move you, you're blocking something. Okay, this looks good. Okay, I won't be able to tell when I'm not showing, but there, I think that's better. Okay, so click on ruler, stopwatch, and period trace. Okay, there's the ruler, there's the stopwatch. The period trace will show in just a minute. Okay, now we're going to start here at length 1. Okay, and that's 0.7 meters. We're going to start with mass 1 kilogram. And we're going to start with Earth. And what is the acceleration due to gravity on Earth? Hopefully you know, right? 9.8 meters per second squared. Perfect. And we're not going to deal with any with friction this time. All right. So there's our setup. Let's go back to, now here's where I run into problems here, is because now I can't go back and forth between my screen sharing. Okay, so let's go back to this. Okay, now it said record the length of the pendulum. Do you remember what it was? 0.7 meters. Oh, here comes Dre back in. So let me get Dre here. I think I already have him present. Got him. Okay, Dre, we're doing Lab 7. You can access that through week 4 instructional materials. Scroll down until you see Lab 7. Okay, the length of the pendulum was 0.7 meters. I have a lot more line there than you need. The mass of the pendulum, remember what that was? 1.0 kilograms. And what did y'all say the acceleration due to gravity was? 9.8 meters per second squared. Perfect. Okay. Now, I'm going to move this down just a little bit here so I can read better. Move the ruler to the left arc and lift the pendulum to about 0.4 meters above the zero reference level. Now the zero reference level is as low as that pendulum can go. And we're going to calculate the maximum potential energy at that point. So that's what we're going to do. So let's go back to our screen share. And there it is, Pendulum Lab. Okay, so let's move the ruler over here. Okay, I'm going to go to the left part of the arc here, right about there. Now, let me just, for right now, move it all the way over. Okay, now you see the pendulum length is, you see that little line there? That's right at 0.7 meters. So that's where that 0.7 comes from, right? So now what I'm going to do is move this back to here, the left part of the arc here. That's at the same level. I'm going to lift this pendulum, and remember that's 1 kilogram pendulum. Move it here, and I'm probably going a little too far. Oh, wait. I didn't mean for that to do that. Stop. Does that, that's not what I wanted. Okay. The trouble is your names are covering what I need to see. So I'm going to move y'all up here. Oh, that works okay. Well, it doesn't work okay. All right, let's stop. Okay, stop it. Okay, now I'm going to move this over just a little bit further this way. This is more art than it is science right now, so sorry about that. So let's move this up until it's 0.04 of a meter. You see, isn't that right about there? Isn't that? Okay. As soon as I let go, it's going to start swinging. But I can't, it's too jittery. Why in the world is this being so, it works so smoothly. So you see, that's right around point, the pause button. Okay. This one right here? Okay, that may work better. Okay, let's see if we can move that here. Look like you're right there. Okay, there we have it. So that's about 0.04, because this is 0.7 and that would be 0.6, so this would be 0.65 and this will be 0.66 here. So the difference between 0.7 and 0.66 is 0.04. You were down here and you've gone 0.04 up. Okay, so let's go back to our screen share. Okay, and it says move the ruler to the left arc, lift the pendulum about 0.04 meters above the zero reference level. Zero reference level is as low as it can go. That was at 0.7. This is 0.04 above that. Calculate the maximum potential energy there. Does anyone remember the formula for calculating potential energy? GPE. That was mgh. Here's the m, 1 kilograms. G, right here, 9.8 meters per second squared. And then what was your delta H? That was this 0.04. Okay, everybody get those numbers? Oh, I'm back to 100% charge. Good for that. Let me log in. Okay, let me get my calculator started. Okay, now, what was your potential energy, gravitational potential energy, GPE, that was mgh. The mass was the mass of the pendulum, 1 kilogram. So I'm going to type in a 1. Okay, that was pretty easy. Times g, what was your acceleration due to gravity? 9.8 meters per second squared, times, and your delta H here was 0.04 meters. Hit equal, and what is your maximum potential energy there? Oh, here, I'm trying to find the thing. Did y'all get something about 0.392? Did anyone? Okay, 0.392. What were the units? Kilograms, meter squared per second, meter per second squared times meter, which is meter squared per second squared. That would be joule. Okay, 0.392 joules. Okay, now what's the velocity of the pendulum up there? It's sitting there. What's its velocity? 0. Okay, so there's that answer. Okay, calculate the kinetic energy of the pendulum there. Kinetic energy is 1/2 mv squared. And if v is 0, v squared is 0, 1/2 mv squared is 0. Right? Yay or nay? Okay. Kinetic energy is 0. What is mechanical energy of the pendulum up there at the top? Okay. Well, mechanical energy is a sum of potential energy plus kinetic energy. And if kinetic energy is 0, potential energy was 0.392 joules, your mechanical energy would be 0.392 joules. Right? Now, again, this is going back to a couple labs ago. What is the mechanical energy at the bottom of the arc? Okay, because mechanical energy is conserved, it always stays the same. The mechanical energy at the top and the mechanical energy at the bottom are the same, so then again it's 0.392, wherever my calculator is. Okay, 0.392 joules. Make sense? Mechanical energy does not change, it's conserved. Now, what's the potential energy at the bottom of the arc? Okay, let's go back to that. I just hit the wrong key. Okay. And I think I messed up everything here. Not quite everything, but a lot of things. I got to move this back to the bottom. Y'all can't see it, but I can, and it messes up what I can see. Okay. Now, remember what the bottom was? The bottom was as low as it could go. That's the 0 reference level. Now let's see, was someone else trying to get in? I don't think so. I think we've got everybody here. Okay. Now, at the bottom here, when this is down here at 0.7, the pendulum is at 0 potential energy. So that was the answer to this question. Okay, calculate the potential energy at the bottom of the arc. There, you're as low as you can go, so there you're at 0 potential energy. Remember that? Remember the skater that we had. As low as it can go, that's the minimum potential energy. Okay. So what's the kinetic energy at the bottom of the arc? If your mechanical was 0.392, your potential is 0, then all the energy at the bottom of the arc is kinetic energy. 0.392 again. Okay? Got it? Yay or nay? Now, based on that, what is the velocity of the pendulum at the bottom of the arc? Okay? Now, well, let's see. Let's go to the whiteboard. Okay? Okay, now I'm going to have to move some things around here too. Okay, and I think I'll move the whiteboard over to the right this time and up. Okay, now, and for some reason my calculator just turned off. There. Okay, got it back again. Okay. I think I'll unplug it because it is getting sort of hazardous. All these wires are tangling each other up. I'm going to quickly go back to where we were. Okay, that's right here. And what we had, the kinetic energy of the pendulum at the bottom of the arc. So that is kinetic energy at the bottom of the arc is 0.392. Wasn't that what we were using? Right or not?
Yes, sir.
Okay. And what is that? That's measured in joules, but a joule is a kilogram meter squared. Get out of there. Goodness gracious, this is a pain in the neck. Kilogram meter squared. Wait. Kilogram meter squared per second squared. That's what a joule is. Okay? And it's also 1/2 mv squared. So that would be 0.392 kilogram meter squared per second squared. Okay. Now, we want to know what the velocity is at the bottom. So the first thing we're going to do is multiply both sides by 2. Okay, so here the 2's go out, and you have mv squared is equal to twice 0.392 would be 0.784. Sorry, I've got a sneeze. Okay, y'all awake yet? Sorry about that. And that would be kilogram meter squared per second squared. Okay. Now, then we're going to divide by the mass because we want to get velocity. Okay. If you remember what the mass is, I believe it was 1.0 kilograms. That's an easy division to make. 1 will go away and the kilograms go away and the masses go away. Everything except v squared is equal to 0.784 meter squared per second squared. Okay, so all we do from that point is pull out your handy dandy calculator, and what I did was double that, so I'm going to multiply that by 2. That's the 784 that we had written down there. Turn it sideways so we can get the scientific calculator and take a square root of that. And what do you get? V is approximately equal to, if I can find my key, there it is. V is approximately equal to, what did y'all get? Anybody? I got about 0.885. And what would be the units? You take a square root of both sides here, and that gives you meters per second. So about 0.885 meters per second. So that is what goes here. Calculate the velocity of the pendulum at the bottom of the arc. That was about 0.885 meters per second. Got it? Okay. Now, the next part really requires more art than science, okay? So I'm going to, for right now, I'm going to leave it unplugged for now. And let's go to the screen share. Okay, if I can find the cursor, there it is. Okay, we'll go back to the pendulum lab. Now, what we're going to try to do here, and this is where the art comes in, I'm going to start the pendulum pendulating, okay? So let's start it happening, and you see the trace comes on. So what I want to do is measure the time from when the trace begins and the trace ends. That's one full sweep. So I'm going to watch for that, and when it happens, I'm going to start it, and when it stops, I'm going to stop it. So let's see if I can do that. Start, stop. Okay, I got 1.65 seconds. Is that what you got? Do we need to take a couple more to see if we got it close enough? So let me clear that, and we'll start again. Nope, I messed up. Okay. Start, stop. 1.60 seconds. Y'all feel like we're close enough? Did y'all record both of those? Anybody?
I got the same on the second one. I missed that one.
Okay.
I recorded 1.65.
You got 1.65. That was the first one. Let's do one more, and we'll go with the middle value then. Okay. Start, stop. 1.63. That is the middle value, isn't it? So let's say 1.63 seconds. Okay. So that's what we'll do for our I'm trying to find it. There it is, yeah. Measure the period of the pendulum with the stopwatch. And we got, what do we say, 1.63 seconds? Okay. Now, let's go back to the pendulum. Yeah, we were 1.65, 1.60, and 1.63, weren't we? So we threw out the high and low and took 1.63. That's a cheap way to do an average. Okay. Now, if one of those was really far off, we would have done another one, but I think they were close enough. Okay. Now, what we're going to do is increase the length of the pendulum to about 0.8 meters. Remember, it was at 0.7, so we're going to increase that. And then we're going to repeat 4 through 12 above, and those will be the same answers that are down here. So let's go back to our pendulum lab, and let's stop it because it's getting tired. Okay, let's stop that. Okay, reset this. Okay, now let's go to make the length 0.8 meters. Well, it's not moving. Oh, there it was. Okay, 0.8 meters. Leaving the mass alone, that type of thing. Okay, let's see what else we're supposed to do. Okay, move the ruler to the left arc and lift the pendulum to about 0.04 again, above the 0 reference level. Now our zero reference level is 0.8, not 0.7, so we're going to have to do some adjusting there. And then we'll go back and calculate maximum potential energy. Okay, so let's go back to the pendulum lab, and now we're going to go up here to, does that look about 0.4? Oops. Okay. Okay, look like we're about 0.4 again. 0.04, I mean. Isn't that right about the right place? Maybe a little bit further. Okay, looks about right, doesn't it? 0.04 again. Okay, so let's go and see. Okay, now what does it say to do there? Calculate the maximum potential energy at that point. Okay, now when that maximum potential energy was m, we didn't change the mass any, 1 kilogram, times g, we didn't change that any, we're still on the earth, 9.8 meters per second squared, and we still got the same 0.04 meters. So our potential energy is the same. What was that, 0.392 was it? Yes or no? Or yes, it was.
0.098, wasn't it?
Okay, that is the g. That is your acceleration due to gravity, was 0.9 or 9.8. But remember,
Yes, sir. It's 0.392.
0.392. Okay. All right. Now, so same maximum potential energy there. What's velocity of the pendulum up at the top? What's velocity of the pendulum at the top? 0. What's kinetic energy at the top? 0. Okay. What would then be mechanical energy at the top? 0.392. Perfect. What is mechanical energy at the bottom of the arc? Okay, sorry about that.
I'm trying to type in.
Oh, I see. Okay. Man, if I were typing, I'd really be moving slowly. So what's mechanical energy at the bottom? You're right, 0.392, because it doesn't change. Mechanical energy is conserved. What is the potential energy at the bottom of the arc? 0, because you're at the lowest potential energy then. Okay, so what's your kinetic energy at the bottom?
0.
No. Remember, potential plus kinetic is mechanical. So that's back to your 0.392, was it? Okay, 0.392. Okay, and then do the same calculations we did before on the sheet here, whiteboard, and it was the same thing. Kinetic energy at the bottom was 0.392. That's 1/2 mv squared. Double that, you get 0.784. Take a square root of that, you get 0.885 meters per second. Same velocity, because you had the same potential energy. Well, potential, but also kinetic energy there. So that didn't change. 0.885 meters per second. Okay. What's next? Okay. Measure the period of the pendulum with the stopwatch. So let's go here. Back to the pendulum lab. And I'm going to start it moving here, and then I will try to do the trace. Start, stop. 1.73. Was I that much worse? Let's see. Start, stop. 1.82. Whoa. Okay. Let's try it again. Start, stop. 1.66. What's the middle value there? About 1.73 or something like that? Did y'all 1.73? Hey, what happened there? Did it slow down? No, the velocity was the same, but the length of the pendulum, that's what determines your period. Not how far it is above the zero reference level. That was the same. It's the length of the pendulum. Okay? And that's indeed what makes the difference with a pendulum. How long the pendulum is. Not the potential energy, not the kinetic energy. It's how long that pendulum is. So let's go back to here and see what the next question was. Okay. The velocity was the same, kinetic energy the same. Looks like everything pretty much was the same. Oh, wait. I'm sorry, I was in the wrong place. Measure the period of the pendulum, number 21. That was what, 1.73 was it? Okay, so that got longer because our length was longer. Okay, so what we're going to do now is increase the mass of the pendulum to 1.5 kilograms. And then we're going to repeat those questions again. Okay, so let's go back to our pendulum. Okay, and let's stop it. It's tired of moving. Okay, let's increase our mass to 1.5 pendulum. Goodness gracious, this is slow, isn't it? Isn't that what I said, 1.5 kilograms? Okay, there we are, 1.50 kilograms. Okay, so let's go back to our sheet here and start filling out the information. Increase that to 1.5 kilograms. Repeat questions 13 to 21 above. Move the ruler to the left end, and we'll keep it at 0.04 meters above the zero reference level. Okay, so what's the maximum potential energy there? Remember what potential energy was? mgh. But now your m is 1.5 kilograms. G is still 9.8 meters per second square. And you're still 0.4 meters above the zero reference level. So that is now going to be 1.5 times 9.8 times 0.04. And what does that give us now? I can't read it. Okay, the maximum potential energy there, 0.588 joules, right? Now that was an increase from what we had before, right? Okay, so what is velocity of the pendulum there at the top? Okay, and you want to have it? Velocity of the pendulum up there at the top. Let me go back and show it to you. Okay, All right. So we've increased the mass, left it at 0.8. So we're going to move this back to the same height, wasn't it? 0.04. Whoops. Okay. Let me see if I can get this to move back up here. Right around 0.4. Okay, 0.04. Okay. What's the velocity right there? Is it moving?
It's zero.
Say that again.
Zero.
0. Perfect. Okay. So that question is 0 because that's the maximum height it goes at momentarily is 0. So that's number 23. The velocity of the pendulum there was 0 meters per second. What's the kinetic energy of the pendulum there? 0. Okay. What is the mechanical energy of the pendulum there? 0.588 joules. Okay. What is the mechanical energy of the pendulum when it reaches the bottom of the arc?
0.588.
Perfect. Okay. And what's the potential energy at the bottom of the arc? 0. Exactly. Okay. So what is the kinetic energy at the bottom of the arc?
0.588.
Okay, 0.588. So this time, to get the velocity, we have a new kinetic energy. So let's go back to our whiteboard. And now, wow, that went up a lot, didn't it? So let's do it over here. You want to do it in a different color? What color you want? We got lavender, we have red, we have pink, we have, say again? Red will be fine. Okay, let me get red back. Okay, so the kinetic energy at the bottom is now, I've got to get my pen. Okay, where in the world is my pen? There it is. Okay, so KE at the bottom now was it 0.588? Is that what it was? Okay, and that would be kilogram meter squared per second squared. Keep up with your units. That's what a joule is. Okay, now, and that is 1/2 mass times velocity squared, right? That's what kinetic energy is. So what we're going to do, I'm going to write it down again, equals 0.588 kilogram meter squared per second squared. Okay, first thing we're going to do is multiply both sides by 2. Okay, and that gives us mv squared is equal to, multiplying that by 2 would be 1 point, okay, that's going to be a 6, that will be a 7, and this will be 1.176, right? Okay, divide that by m, and that would be kilogram meter squared per second squared. And our mass was 1.5, wasn't it? Kilograms, right? And what do you get? The masses divide out here, and you get v squared is equal to, someone, this is so aggravating. Okay, if I can find my calculator now. Okay, 1 point, don't want to drop that pen. Okay, it's expensive. Okay, I'm cheap. Okay, so it's 1.176 divided by 1.5. And what do you get? 0.784 again. That's what we had v squared was before. 0.784 meters squared per second squared. Okay? And guess what? You take the square root of that, and you get right back what we had before, 0.885 meters per second. So guess what? It doesn't matter what the mass is. All that matters well, okay, we'll come back to that in a minute. What matters is the length of that pendulum. That's what determines the period. The kinetic energy increase, but here's Tobias. He must have had to step out, and he's back in again, and I can't get the cursor to show up. This is aggravating about this thing. Okay. This is so aggravating. Okay, I'll do it this way. Okay. So Tobias is back. I had him here before, and he's back again. Good deal. Welcome back, Tobias. Sorry it took me a long time to get you to come back in. Okay? Now, I'm sorry. That happens. Didn't have it happen today, but about once or twice a week that happens with me too. Maybe not quite that frequently, but at least one time this week it has happened. Oh, it was in this class too, I think, wasn't it? Okay. So here we are back to here again. Okay. We calculated the kinetic energy at the bottom of the arc. This is when we had gone up to 1.5 kilograms. We calculated the velocity at the bottom of the arc, and it was the same thing, wasn't it? Okay. And now we've got to measure the period of the pendulum at the bottom of the arc. Okay. So let's go back to our pendulum, and I'm going to set this down, and I'm going to set this down because I don't need any distractions here. So we're going to start it pendulating. We're going to reset this to 0. Okay, and then at some point here I will start it again. Start, stop. 1.81. Did y'all write it down? That's seconds, right? Okay, let's do it again. Start, stop. 1.70 seconds. Okay, reset. Start, stop. 1.73. Hey, look at that. What's our middle value?
1.73.
Even with a bigger mass on it, it didn't matter. All that determines the period of the pendulum is the length of the cord. It doesn't matter how much mass, it doesn't matter how much potential energy, it doesn't matter what angle you start with. All that matters on the period is the length of the arc. Okay? Now sure, potential energy changes, kinetic energy changes, all sorts of things change, but the period of the pendulum, all it depends on is the length of the arc. When we lengthened it, we got a longer period. When we shortened it, we got a shorter period. Okay. Let's see. I'm going to stop this for a moment. Okay. And let's go back and see if we finished the questions. Okay. All right. Oh my goodness, look at that. That's not supposed to be there. Okay. Measure the period, and we got what, 1.73 again? Does the period of the pendulum seem to depend on the mass of the pendulum? Yes or no? Say again? No. Okay. On what parameter does the period of the pendulum seem to depend most strongly? The length of the length of it. Exactly. And I'm sorry, folks, I didn't realize these were still here. That was left over from last time. I'm going to get rid of these now. That's not part of today's lab. Sorry about that. Yeah. How can I delete those? Okay, there we go. Good deal. Now, there's today's lab. And unfortunately, there I've gone and cheated you out of another hour of your tuition dollars now. Sorry about that. But we're through. Are there any questions on the lab?
No, we have a few more, right?
A few more labs? No, those other questions, I didn't realize they were on there. We ended at 32. Sorry. I just hadn't noticed that those were there. Those were left over from the last lab. So, see, I use, it's just easier to type them then using the previous lab, especially because of the very top. That doesn't change much. Okay. Any other questions? Did this lab make sense? So if you have a grandfather's clock or a grandmother's clock that you have that pendulum, if you're trying to get it to go faster, then screw up on it some, go slower, screw down on it some. We have a grandmother's clock downstairs that as far down as I can go, it always was running slow. Okay, never could get it to run on the right time. So after a while, we just use it as decor down there because you never could get the time to be right. Okay. So anyway, any other questions? Okay. Are you all right with this? Sorry that I left some questions on there I didn't know were there. All right to go? Did anyone need another part of it gone over? Anybody? Okay, it looks like we're losing people. So I'm going to stop sharing if it's okay with you. If you need any other questions, I'll be glad to try to answer them. But we're down to 6 people now. Any questions? All right. Have a good, safe weekend. It may be beautiful weather and stuff like this, but be careful. The virus is still there. Okay? So take care. We'll see you on Tuesday. Okay? Some of you I'll see, well, earlier on Tuesday, but I think all those people have gone now. All right. Take care. Be safe. I can't get it to end. There we go. Bye-bye.